Good morning.
Thank you. Put it in the folder VPO with all your
Everybody. I hope you all had a very good time last night.
Yes.
Good. Good. Yeah.
Oh, yeah.
And welcome to Pablo, who has joined us. Thank you. All right. It's fine, we understand. Okay, so this morning I am talking about linear optics and just the mechanics behind it, how it works, and how we use it. So I'm going to start with two-dimensional linear optics. So in essence, I'm working with Gaussian systems, centered refracting surfaces that are spherical. We are, of course, linear optics based in first-order optics or paraxial optics. We find that it is simpler and much more powerful than traditional paraxial optics. And also, just to make the point that optics is a lot more than just power. And it incorporates, so linear optics incorporates all the properties of a system, not just power. And we base it on two concepts, the optical system and the ray. So a system, something tangible, and just a little bit of definitions. We define an entrance plane, we define an exit plane. We have a longitudinal axis, not necessarily an optical axis. And I always tell my students, it's kind of like the lines of longitude and latitude that don't really exist, but we need a reference lines to measure from. And then we talk about upstream and downstream. And of course, we've got our refractive indices outside. And what you see between the entrance and exit plane is the system. Could be absolutely anything. So I think most of you have seen the ABCD matrix. Bill Harris likes to call it the transference. It's also known as the system ray matrix or the ray transfer matrix. And these are the names that Bill gave each of the elements of the transference. We have dilation, distribucy in meters, divergence in diopters, and divarication. And I will come back to the meanings of those a bit later. The ray, we define the ray as what's happening exactly at the point where it meets the entrance plane, and we can define it as its position relative to the longitudinal axis and its inclination also relative to z, giving the state of the ray as y naught at alpha naught. And then we do exactly the same thing on emergence. We want to know exactly what happens to that ray as it emerges in terms of its position and inclination. The effect of the system on the ray is defined as S times rho naught gives us rho. So S tells us what the effect of the system is on this ray and how it will emerge. And so if we multiply that out, we get to equations, which we will use a lot this morning. We all know there are two elementary systems, the homogeneous gap and the refracting surface, and any compound system is made up of a combination of these two systems. And for linear optics, we need to choose very carefully what we're going to include or exclude from our system. So let's just have a quick look at the transference for a homogeneous gap. And we have a gap of width z. And we have this relationship of the inclination, of course, doesn't change but the position will change. So homogeneous gap is just a position changer. And if we line up, so we've got alpha naught equals alpha, and we line up this one, and from this relationship, and this is what the transference of a homogeneous gap looks like. The refracting surface, of course, we're all very familiar with. We define the refracting surface as a system with zero gaps. So we're drawing our entrance and exit planes in an exploded fashion. And if we line up our two equations, we know that refracting surface is an inclination changer. So this is the relationship that we get from a refracting surface. And of course, the position doesn't change. And that allows us to obtain this relationship for the transference of a power refracting surface. Compound systems. If the system one changes the ray across the system, and there's no gap here, and that is the effect of system two, then of course we can substitute and we obtain a relationship of S2, S1 times rho naught equals rho. And the important thing to pick up here is, of course, multiplication in reverse order. And that allows us to obtain the transference of as many elementary systems as we need. Right. So the transference has fundamental properties. The A, B, C, and D are the fundamental properties. And according to Bill, it completely characterizes the first order nature of the system. All the other properties can be calculated from the transference. Very nearly all of them from the transference alone. There's, I think, one where you need one more piece of information, which is the length of the system. Otherwise, you can obtain all the derived properties from just the transference. The power of the system is in fact a derived property. So the power F is negative C. So power itself is a derived property and not a fundamental property. Symplecticity, so the transference belongs to the Lie group, the symplectic Lie group. So all transferences are symplectic, and a symplectic matrix with the correct units represents an optical system. For a Gaussian system, that simplifies very simply to the determinant is 1. Okay, so we can check that. We've got two elementary transferences. Each of them has determinant of 1. And we also have a relationship that determinant A times determinant B is the same as determinant AB. So it doesn't matter how many elementary systems we multiply together, we will always get a unit determinant. Right, the transference of every optical system is symplectic, and every symplectic matrix is the transference. I actually said that already. Every optical system will have a single unique transference, but a transference is not the same the other way. So a transference could be represented by or represent a number of different optical systems. Each of those systems will have the same effect on light, but it will be made up of slightly different components. A very simple example is a thin lens. Power of 8 can be made up of 4 plus 4, 5 plus 3, etc. So the entries are slightly different, but the transference will look the same and represent each of those different forms. Right, we have 4 special systems. So the fundamental properties can have any value. It can be positive, negative, or 0. provided that the symplectic relationship holds. And systems for which the fundamental property is 0 represent special systems. I'm going to go through that. We're going to make use of the two basic equations as we do this, and we're going to consider each of the A, B, C, D, equating it to 0 and see how it affects the system. Right. So we're going to start with A equals 0. And if we substitute A equals 0 into here, we are left with B alpha naught equals Y. So let's send a ray through our system with a particular inclination. And let's send a second ray through the system with the same inclination. And we find that it exits at the exact same position Y. And the same for a third ray. So we've got a very appropriate name, exit plane focal, meaning we're focusing at the exit plane. A nice example of this is an inotropic eye, or indeed a compensated eye, or compensated for distance, of course. Right, let's look at a conjugate system. So if we substitute B equals 0, we're going to get A Y naught equals Y. And if we send our rays through it, we're getting this effect. So all rays that are at make a focal point or an object point at the entrance plane will make a focal point at the exit plane. And you can see that it is conjugate. Okay, so this is the typical system that we work with when we first start learning about optics at university or even at school. So an example, of course, is also a myopic eye, where this is an object and you've got a gap and then you've got your eye. Okay, and if I rearrange A Y naught equals Y, you've got the very familiar transverse multiplicator magnification equation. So we can say that for a conjugate system, A is the transverse. If we substitute C equals 0, we're going to get D alpha naught equals alpha. And if we start sending some rays through, we are getting an afocal system. All right, so we all know this one, afocal telescope. We're familiar with it. And if I rearrange our little equation, we get our angular magnification. Okay, so when C equals 0, D is representing your angular magnification. Right, and for D equals 0, we've got CY naught equals alpha. We can send some rays through, and all rays that have the same incident point or object point will emerge parallel. It's the least encountered of all the 4 systems in optometry, at least, but you could look at this as a patient's eye where you're doing retinoscopy, so it's a reversed eye, and so on. Okay, right, Bowles nomenclature. Dilation, he's basically looking at the change in the position of Y, or if you prefer, the width of the aperture, or the width of the rays to the width of the rays. He also calls it the ametropia as a ratio, as opposed to referring to refractive error. So B, if B equals 0, we have a conjugate system. So when B is not equal to 0, we have a disjugate system. And that's where the word disjugacy comes from. C, divergence. So we talk about a positive power having a converging effect on the divergence of light. And so if C is equal to minus F, then C, positive C, would have a diverging effect. So we're calling it divergence. And then divarication is merely the spreading out of light rays, creating a wider beam of light after passing through a system. Okay, so if you look those words up in the dictionary, you'll actually see where Bill got those words from. Okay. Right, deriving properties. So I'm just giving you a few steps. So the first thing is to just look very carefully at your system and define very clearly what you're working with. What's included, what is excluded, where are the rays, where are they making a focus, and where are they parallel, because then we can use one of the 4 special systems to investigate an unknown property, for example. All right, so I'm going to just go through a few examples, familiar examples, just to get a bit of a feel for how these transferences work. So, power of a thick lens, there we have our system, F1, a gap, and F2, and that is how we're going to define the system in terms of entrance plane, exit plane, and longitudinal axis. To obtain the transference, we multiply in reverse. So we're starting with F2, then our reduced distance, and then F1, remembering the minus signs. Multiplying that out. And we look at C in particular, and that should already start to look familiar, remembering that F is equal to minus C. If we substitute in, we have the familiar thick lens equation. Right, refractive compensation. So we've got our system, our eye here. We've got a compensating system, thin lens. We're working at the cornea. You can change that, of course. You can do what you want. But we're going to just put a thin lens juxtaposed to the cornea. And we need light from a distant object, focusing on the retina, define our system from in front of that thin lens to just before the retina. And that is an exit plane focal system, so we set A equals 0. We then set up our transferences, so multiply from in reverse. We've got the transference of the eye, we've got the transference for our thin compensating lens, and we multiply through. We only need A. We don't need these other 3. So we solve for A. We've got this relationship, and we solve, and we very simply get A over B. Okay. What's interesting to note, however, is that the power of the eye is not involved in the compensating power. Let's solve for the power of an intraocular lens. This patient would like to see at distance. Again, we've got a exit plane focal system. We define our system as just the eye, and we set A equals to 0. We can now set out all our transferences. So we've got our posterior, our vitreous chamber, our unknown intraocular lens power, aqueous chamber, corneal power. So, or multiply out, and we only need A, of course. So we can now set this equal to 0 and solve for the intraocular power, which in this case is 15.43. Intraocular lens for reading, we're going to have something slightly different because this patient is reading at near. Now, if you look at the rays, we're sitting with a conjugate system this time. So we define our system as from the object, including our working distance. So that's now going to be included in the system, and we're going to be solving for the intraocular lens power. We need to set B equals 0, set it up, multiplying from reverse vitreous, intraocular lens, aqueous, cornea, and working distance. and set B to 0, and this time the intraocular lens needs to be 19.06 diopters. All right, let's have a look at some of the derived properties. I'm going to start with back neutralizing power. So this is going to be any optical system. For neutralization, we need to set C equals 0 because we want to end up with an afocal system. Set up our system, so multiply in reverse, solve for C or multiply for C, and we have a back neutralizing power is simply C over A, and of course our back vertex power will be the negative of the back neutralizing power. So we've done 2 in 1. Front neutralizing power, we're doing exactly the same, but in reverse. We're going to have C equals 0, solve for C, and we've got front neutralizing power as a relationship of C over D and the negative of front vertex power. Magnification and blur. Right, for magnification and blur, we now need an aperture, a pupil. Okay, so we're going to look at the magnification and blur on the retina. We've got the corneal plane, we've got the pupillary plane, and we've got the retinal plane. And that means that we're dividing the system into an anterior and a posterior system. We are interested in what the ray is doing at 3 positions: at the cornea, at the aperture plane, and at the retina. And so we have the state of the ray in 3 different positions. Now, what we want is we want to know what the inclination of the ray is at the cornea, the position of the ray through the pupil, and the position of the ray at the retina. So we take our 2 equations and we substitute and manipulate. I'm not going to go through all of that. That's a whole chapter. Okay. But we end up with this little relationship here. YR, our retina, as a relationship of YP through the pupil, and alpha K, the inclination at the cornea. Our subscripts is E for eye, A for anterior, P is pupil, B is posterior, A, of course, anterior, and K is cornea. Okay. From that, let's just take this relationship, AE over AA, and we're going to call it WE, the distance image blur coefficient. And then we take B posterior over A anterior, and that is XE, the distance image size coefficient. And we get this much simpler looking relationship. Okay, so how do we interpret this? Here we have the cornea, we have the iris and the pupil, and we have the retina, all very exaggerated, of course, and our relationship. So let's define first our chief ray. So we're going to be looking at the position right at the center of the pupil, and we want to look at a ray coming in straight on, and the chief ray, and of course it's going to land at this position on the retina. If we look at marginal rays and you take the diameter of the pupil and we send in a pencil of rays, obviously not all the rays are going to reach the retina. We're going to get a blur patch that looks like that. Okay, so if we look here and we work with WE times YP, and instead of YP, we're working with delta YP. So we're working with the diameter of the pupil. Here we go. Okay, then the diameter of the blur patch is simply YE times P when alpha K equals 0. Okay, so we're ignoring this component, only looking at the size of the blur patch, the diameter. Okay, Now let's look at a ray going through the center of the pupil, and it lands at this position on the retina. This distance from the center to that point on the retina, this pink dashed line, is of course the difference in inclination between our chief ray and this one, and which of course indicates the angular size of an object. Okay, so this dashed pink line is giving us the image size on the retina, and that is going to be XE alpha K. So this component, when you're working with the chief ray, in other words, YP equals 0, this component gives us the image size. And if we send a few more rays in, well, we've got another blur patch up there, and we can then see whether those two blur patches are overlapping or not overlapping, and whether two point objects, maybe two stars, are visible as separate, or if they're just a blurred blob. All right, we can also derive the positions of the cardinal points, because you'll have noticed that I haven't used cardinal points to get any of the transferences. Cardinal points can be derived from the transference. So we define a nodal ray as A naught equals A. So a ray aimed at N naught emerges from N with its direction unchanged. And of course, we should all know that's a nodal ray. And of course, we have an optical axis, which is also a nodal ray. So from our equations, if we look at that little relationship and this relationship, we can do a little bit of manipulation, and we get a relationship. So we multiply both sides by 1, by N naught over N naught and N over N, and we get this relationship, which we're going to say that X is this ratio, N over N naught. Okay. We can now substitute this relationship into here. So we've got, instead of alpha, we've got X alpha 0. And a little bit more manipulation, which I'm not going into. That's again a whole chapter. We get this equation or relationship, which is defining a nodal ray. So if a ray obeys this equation, it will be a nodal ray. And there's an infinity, as we know. Right. For anterior chamber, anterior cardinal points, we have this relationship. So Z is the distance from the entrance plane. And if we substitute N over N naught for X, we can then find the position of the nodal point. If we substitute 1, in other words, now we're looking at alpha naught equals alpha as opposed to A naught equals A. If we substitute X equals 1, we will find the position of the incident principal point. If we substitute 0, we will find the incident focal point position. So all three of them are coming from, all three incident cardinal points are derived from that single equation. So there's a very definite relationship between all the cardinal points. They're not independent. We've done a similar manipulation, and we have got the position of the emergent cardinal points measured from the exit plane. And similarly, if we substitute N over N naught, we'll get the nodal point, emergent nodal point. Substitute 1, we'll get the principal point, and substitute plus minus infinity, or 1 over X equals 0, and we will get the emergent focal point. Right. And that's pretty much what it's going to look like. Okay. Quantitative analysis. So our power matrices define a vector space or a linear space and can be used for quantitative analyses. We do this all the time. We can also graph them in 3 dimensions if we so wish. The transference, on the other hand, because it's a symplectic matrix, does not conform to a linear space. And we cannot simply average symplectic matrices because the result will not be symplectic. So we need to use a little bit of a trick, and that is to transform the transference into a vector space. For example, be it by using a Hamiltonian matrix or an inner product space, and that will then allow us to do quantitative analysis in the with the Hamiltonian matrices, and then convert them back to a transference to a symplectic matrix, and then we are able to do quantitative analysis. So the relationship between a transference and a Hamiltonian or symplectic matrix and a Hamiltonian matrix can be obtained through the Cayley transform. It can be obtained by the log and exponential matrix, which of course is pretty simple on a software like MATLAB. Right, so far we've been working with Gaussian systems. I want to now start generalizing to astigmatic or systems with astigmatic surfaces. And so we're now working in 3 dimensions. Our position of the ray Y is defined as a vector, and our inclination is also defined as an angular vector. And so we have our ray where each of these 2, you'll see they marked in bold, each of these 2 is a 2 by 1 column vector. And of course the same at the exit plane. Astigmatism. We define astigmatism of a surface in terms of a power matrix. And so we have got the transference as A, B, C, D, where each of these entries is a 2 by 2 submatrix, and S becomes a 4 by 4 block matrix. When we have heterocentricity, we can define a little vector called delta, E and pi, pi simply being the Greek representative of the letter P, because it's going to be a deflectance or prismatic effect, and E is going to be the transverse translation in terms of the amount of decentration. It then becomes an additive component, which makes things a little bit messy. However, we can combine it into the transference to create an augmented transference. So we've got A, B, C, D, E, pi, and a trivial row. So it maintains, it's a square, it's still a square matrix, but it's augmented because a 5 by 5 matrix is not symplectic. Only matrices that have equal numbers of rows and columns. So this transference component is symplectic, but this we refer to as an augmented transference. All right, so symplecticity, when we are generalizing and we're now working with 4 by 4 matrices, this is the definition of symplecticity. So transference, transpose E is equals E, where E is equal to this value. Now, in a lot of texts, it's called J, but we like to use J for something slightly different, and so we've called it E. And from that, if we multiply out, we obtain 3 relationships. So if a matrix obeys all 3 of these matrices, all 3 of these equations, then it is a Bailey symplecticity. And you'll see here something that looks a bit like the equation for the but a little bit more. Right. Let's look at some of the derived properties or summarize the derived properties. We said that the refractive compensation at the corneal plane is now B inverse times A. We can't divide anymore, we have to inverse. The power of a thick lens generalizes. It looks almost the same as for the Gaussian system, except we need to worry about the order of multiplication here. So it's F2 times F1 with the reduced thickness. Magnification and blur generalize very simply to look like that. Okay. And the cardinal point positions look like that, with C being inverse from the front. And that's the transpose. And Z would be, if you use the eigenstructure, you would be able to then obtain the position of, let's say, a node. Okay, it's no longer a nodal point because it's going to split up similar to an interval of Stern, but the lines don't have to necessarily be orthogonal to each other. So it becomes quite interesting when you look at those points. And in conclusion, our fundamental properties altogether completely characterize the first order optical nature of the system. All the other properties are derived properties, and we can derive them from the transference. We need to carefully define our system, what we're including, what we're excluding, and the easiest to try and understand the system is, of course, start with the Gaussian and then go on to the generalized system. And the transference itself will completely define the effect on the rays traversing the system. Are there any questions?
I have one question.
Mm.
Well, this is great. I really love it.
Mm-hmm.
But I have a kind of practical question. Are you teaching this approach to optometry students?
Yes, in second year. There they all are.
You are very brave. I think it's very useful, but I cannot imagine most of our undergraduate students, they are the optometry students, just going through this. Only really a few. So I think it's, although this can pay later, right? If they learn this, it's going to be very easy to do many things. But I can see in many cases a kind of a gap. They don't really, cannot really prepare. I think so that's the reason I think it's very useful, but also I think it's a little bit difficult for us. That was more a comment than
Okay, thank you.
I also want to make an echo. Just then I talked with Andrew whether we can follow the lecture or not. To be honest, I cannot. But I really love it, and I think this is very fundamental for optics. As trained as an ophthalmologist, I only learned a very little optics when I was in university. So my question is for the optometry students in the university, how well you can understand what is Tanya is talking about. It's very, very fundamental and important. And I also want to ask the opinions from the famous optics professors, whether this is how difficult or how basic it is in the optics area.
Okay.
Before the students answer, I can say from the university perspective, ophthalmic optics has got the highest failure rate, the most tutors. It is a challenging subject, but Tanya is really doing an excellent job with that. But now the students can answer.
Let's start with this.
Lovely presentation, Dr. Tanya. Honestly speaking, I think she makes it so easy to understand. And I think it is a privilege that we get exposed to this kind of information in our second year already. so that by the time we are ready to undertake any form of research, we have a deeper understanding and insight into the field of ophthalmic optics, and we are able to contribute to the field. But in a nutshell, sorry, she makes it seem so easy. Thank you.
Thank you, Dr. Tanya, for the presentation. Well, as everyone knows, it's so difficult to understand, more especially in our second years. We're still not sure why we have to learn it. We don't understand the lesson, but later on the years, you will always remember those ones. For example, if you want to learn about matrices, if you get to 4 years and you are fitting contact lenses, the powers of the contact lenses and don't have the same meridians or axis, then you can use the matrices to actually add to get your final power or the final order of the contact lens. So in second year, I would say, yeah, we just pass, but we don't understand the lesson. We understand the lesson later on when we get to 4th year or 3rd year. Yeah, thank you.
Sorry, I just want to add onto that as well. When we do it as well, it's not as compressed as it is now. So it is in sections as well. So then maybe we would start with a very simple equation and then we'd go and build and build and build. So then the understanding kind of flows into it as well. So then you can interchange with all of that. So it becomes a bit easier and a bit more comprehensible.
Just to add one more, I once scored 99% with this test.
You were the only one, Adam. The only one.
If I can just say that I compressed an entire term's working to 45 minutes. So it was very much a crash course on linear optics, just to give you a little bit of a taste of what we do with it.
Yeah, I totally agree. This is very important.
Yeah.
That's
Thank you. Okay.
only my problem.
Any other questions?
Right. Yes.
In the same sense, they undergrad students encounter matrices in this course, or they have learned about matrices before, and do they learn vector space?
So the basics of vectors is already done in school. But because we're working with pretty high level matrices, so I mean, some of what we work with, Hamiltonian matrices and so on, you would only learn in 4th year. So instead of sending them to maths all the way up to 4th year, I give them just what they need in terms of matrices. So that's a fairly comprehensive chapter that I do. And then I move on to power matrices for a term. And then I move on to transferences for a term.
And then Alan takes them.
Yes. Yeah. Well, a CP is doing optics at the same time. So we have optics and ophthalmic optics. So they're learning everything that they need to, all in second year.
I would say in American optometry schools, this would be overwhelming. So you guys are far ahead in terms of understanding. And I've been on several times been asked to review papers from Bill and Tanya and stuff, and I pass them on to Larry. So I wish I would have learned this more deeply. I didn't. So you guys have are in an enviable position to have been taught this.
I think one of the things that makes it difficult for optometrists and ophthalmologists or anybody in general to kind of follow the logic of this system or this approach is maybe a defect of their background in mathematics. Anyone who's had an undergraduate course in linear algebra will have a great advantage because you'll understand things like what is a vector space and how do I make transposes of matrices and what does simplicity really mean and all that kind of thing. This is are the language and jargon of mathematics. And it's been applied to an optical system that we're all interested in. I am more interested in the optics than you are the math, but it's like math is the language of science. And so you have to understand a little bit about linear algebra before you can keep up with what's going on. But my overall impression of it is that it's paraxial optics. It's like ray tracing, mathematical ray tracing, where you replace Snell's law instead of saying it's all the sine of theta, the angle of incidence and the sine of the angle of incidence, make a small angle approximation. So sine of theta becomes theta, and then all the math becomes simple, and that's why linear algebra can be applied. And if you're not willing to make that approximation, then it's like, well, you wonder what it's good for. But I can add a vote of confidence that at any, even in a crazy eyeball with all these aberrations and whatnot, locally, you can still apply the notion of paraxial optics. Because it's about a small area, one at a time. And like I say, Euler's famous theorem of differential geometry says that any smooth surface locally is spherocylindrical, in which case we can apply this methodology, you see. But it would have to be repeated many, many, many times over a highly aberrated surface to put the full picture together. And one thing that I do see missing in the analysis of the kind that Gene and Bill have done for so many years is an attack on imaging. The whole purpose of an optical system is to create an image of an object. And I'd like to see more of that kind of approach. What does the image look like when you use this approach to calculate? You see, it includes all the properties of an optical system. Well, that sounds great. So show me an image. I want to see what the image of an object looks like as a result of using these tools. And I think that would make people more interested in trying to conquer the approach. That's my view.
Okay, so next, Jos is going to pull a transference apart and inspect each of the A, B, C, and D, and try and interpret them.
Thank you very much. I'm a little bit nervous because I'm going to discuss ABCD in, well, pretty much the home of ABCD. And I'm still pretty much a novice in this thing. So please forgive me if I make any massive errors. I try to avoid them. Before I get started, I should give a little warning. Anyone who cannot handle equations, please leave the room right now. Also, anyone suffering from this thing, which is a fear for long and difficult words, same thing. There tend to be a lot of those in this presentation. Okay, like Larry just now said, there is everything is based on Snell's law on a very local scale. So if you zoom in really, really deeply, anything becomes pretty much a plane. So Snell's law applies very locally on each of the spots of your surface. And you can take this in two ways. Either we call ray tracing, which is something that Larry and Ray do a lot, or you can go the other way with ray transfer matrices, like what's done right here. Tanya already explained this. Any optical system can be considered as an entrance plane and an exit plane. You have some ray coming in, you have an X location that can be in 1, 2, 3 dimensions, doesn't really matter. And an angle, also 1, 2, 3 different angles. All of that is possible. And then you have at the other side, you have corresponding exit ray. And whatever happens in between is a black box. It doesn't really matter as long as you know what goes in and what comes out. The rest, not very important. That's what this thing essentially does. You have coordinates, you have slopes. These can be multiple coordinates. These things can be submatrices. All not really much of a problem. Tanya already explained these things.
quite easily. Since if you multiply all these things, you get a linear equation, you get linear optics. Still so far pretty basic. These should also be very familiar, especially to you guys. Basic refraction is the C becomes that particular formula, or much simpler, the negative of the power. And well, if you multiply that, you get something like this, which makes total sense, that the angle, in case of a refraction, it's the angle that changes, but the position that remains the same. You can go the other way around. If you have a transit, you have the, a little bit too far, you have the d, which is the distance of the transit divided by the index, or the reduced distance tau, and you can multiply that, and then you get this. So if you have a ray going over a certain distance, it's not the angle that changes, it's just the elevation of that ray that is changing. So far, it still makes sense, I hope. So the four special systems that Tanya mentioned, I think I can go over it quite quickly. So at the entrance and exit plane, you can have two situations, two special situations. Either it's a parallel beam entering there, or you have a focal point exactly there. So the first one, it could be like a parallel beam entering an eye, and this would be the retina. There you have a focal point, so that's essentially ametropia. Another one is if you have at the beginning of your system, you have a focal point, and you have another one at the end of your system. So essentially you're reading, and then through reading glasses and the optics of your eye, it projects a conjugate image of the page that you're reading onto your retina. So this is the page, that's the retina. So it's conjugate, essentially it's reading. The next one is when you have an afocal system, you have a parallel beam in, parallel beam out. That's a telescope, just like Tanya said. And finally, Tanya called it a ophthalmoscope. I would call it an aberrameter. So like was said yesterday, you have a laser beam coming in, you forget about that. So you have a point source on the retina, which is spreading out in all directions. And at the end of the eye, you get a more or less parallel beam coming out. So it's essentially an ophthalmoscope or an aberrameter. It works in both cases. So we have ocular interpretation. We have all these four names, but my question is, well, what do these words mean, right? I don't really understand these words very well. I know dilation, I know what dilation means, I know what divergence means, but it doesn't seem to link very well to what these things do. And I was told that Bill really took a lot of care in choosing these words, but well, I'm not inside Bill's mind, so it's a bit hard to interpret. So, and I have a second question. Why don't these words start with ABCD? You know, you could have done that effort, but it might have been a bit difficult. So are there any other ocular interpretations? So I forget about, you know, this can, I don't know who started with ABCD. It's at least 100 years old as far as I know. It's Bill that brought it to ophthalmology, at least brought it back to ophthalmology and developed it further. So apart from these four names that we have, are there any other ocular interpretations? So this is a question Tanya visited us in Antwerp a while back. I kept asking her, like, what do these things mean? And well, apart from these four words, she couldn't really tell me either. And you know, it's kind of a life's work. So we started to do it in a different approach. I work a lot with Gaussian optics, so I thought, well, let's do some Gaussian optics with it and see where it leads. So I start with a very simple optical system, very simple. Just a cornea, a lens, both thin structures with a distance, anterior chamber depth, TA, and a posterior chamber or vitreous TV. That's the essence of it. So we have a power PC, a power PL for the lens. The total power is PI. These are the distances in between. If you add them up, you have the actual length and the integers. That should all be pretty clear. Another thing that we need here that will become quite clear later on are the formulas for the principal. We're going to use these forwards and backwards a couple of times to make it. So, okay, like Tanya said, we start with the refracting element. So just the lens, the cornea, the lens, and the distance in between the anterior chamber. Just to keep it simple. Essentially, what you're creating here is a thick lens, right? You have two lenses and a distance. So like Tanya said, we need to multiply backwards. So cornea, the transfer, and then the lens. That looks like this. And if you multiply all these things, then you get something along this line. And these are the A, B, C, and D. Note that these have all colors. I just try to color code them to keep them separate, just for simplicity, as much as we could call this simple. So there's one thing that you can immediately see is very simple. It's just a single character. So the B corresponds to the reduced thickness of the anterior chamber. That's very quick, immediate interpretation. The second one is the C. If you look very carefully, you got PC, you got PL, and the multiplication. Only the sign is wrong, but it's essentially the thick lens equation, but negative. So it's the total power of the eye in this case. So far, so good. We're on a roll. Now we come to A. So what is this thing? Well, it's the tricky thing is it's this distance thing here multiplied by PC, which we can rewrite. So we multiply by PI divided by NV, and as long as you divide by the same thing, it's no problem. And then we can use the principal point, the second principal point of the eye, and then we can take that PI by PV, we put it outside, and we can replace this one by the back focal point, because this thing equals back focal point. I can explain everything step by step, but it might take a bit too long. But this is correct. So, and this can be rewritten as PI by the back vertex power, sorry, of the eye. So that is the power of the eye at the lens plane. So this is pretty much the endpoint of this equation. And when it comes to D, if you look at D, the equation for D is pretty much the same thing, except here it's with PL. So you can do the whole thing again, and it's the power of the eye by the anterior vertex power. So power of the eye at the corneal plane. So does this make sense? Well, if you use proper linear optics, the equations that Tanya showed earlier, then yes, it does correspond. So it's a sanity check. Whatever I came up with here does make sense within the framework of linear optics, even though I strayed a bit from it. Okay, so now we just essentially have a thick lens, right? Corneal lens and the distance in between. So, but that's not what we have in an eye. In an eye, we have a retina, and that is at a certain distance indicated by the vitreous chamber. So let's do that. So we have the S op from the previous slide. We multiply it by SV, the transference for the distance across the vitreous chamber. So we have this thing, we multiply it, and these things become a bit more complicated. Interpretation-wise, there are two that we can immediately already assign. The first one being C, it's still exactly the same thing, nothing happened there. And D is still the same thing as on the previous slide. So that much is easy. Now we come to A. A looks like this. You see both terms have PI, so we can put that outside. Then we have, you need to do a little trick here because the vitreous chamber depth can be written as the difference between the axial length minus the anterior chamber, right? That's what we did here. And then with that, we can come to this equation because the axial power or the dioptric distance is basically the power that an eye needs in order to be ametropic. That's the essence of it. So it can be written as the axial length minus the anterior chamber depth plus the principal point, the back principal point, right? Because the back principal point is actually a negative quantity and needs to be counted from the lens in this case. So it's essentially this distance plus vitreous chamber depth. So we have this this thing here, and in a recent publication, I derived that that's essentially the refractive error divided by the axial power. Now, one of the things that was already clear from comparing ABCD to actual data was that the A must have been related to refractive error. As was already said, if the A equals 0, then the focal point is nice on the retina. So that much made sense. And Tanya also indicated that if there is a refractive error, then it moves either forward or backward this focal point. So it's not the refractive error, it's the refractive error divided by something, in this case, the actual power. And then B, that's a strange level thing. We have this equation, that's just this one here. Here we have the principal point of the anterior principal point. We can split it up again using the equation from before. We have these PI's that can be removed, so we can rewrite it to something like this, which can be rearranged to this, and this looks remarkably like the thick lens equation. Except here we're not talking about powers, here we're talking about reduced distances. So what is this thing? Well, for now we call it tau I. It's like a reduced distance of the eye, but what it means. We tried, this is just the two lens version or two thin lens version. We also tried these equations with 3 surfaces, like a thin cornea and a thick lens, and even 4 surfaces. But these equations become quite complicated. One thing that we encountered there was that in this tau I, there was something along the line of a equivalent power, a principal power. So like there's a principal plane or principal point for the total power or the equivalent power of a structure. Here there is an equivalent, principal power having a very similar structure. So what does it mean? Well, we've been trying to think of this for 6 months or something like that. We're still not out of it. So we have a couple of very specialized people in linear optics. So hopefully you guys have some kind of idea. So at this point, I need to ask you, are you still with me? Okay. So a little overview. So we have the A, which corresponds to the ratio of the refractive error to actual power, and which I already mentioned is linked to the retinal blur size in a different paper. It takes me a bit longer to explain that, but you can look it up. So here we have the equivalent reduced distance, whatever that means, and it's linked to principal powers, whatever that is. The negative of the total power, this is the one thing that we already knew. So that's easy. And then we have the ratio of the whole eye power to the vertex power at the corneal plane. Again, that's a proportion. We're not entirely sure what it means, but at least it's something that can be interpreted. So let's see if this holds up, because so far it has been nothing but equations and everything. So I just had a bunch of syn dyes. They're synthetically generated dyes. The advantage of these things is they have lens radii. So, and we could have a 4-surface eye. Whatever works here should work for real measurements as well. So we have the 2-surface version of these syn dyes. We put them in the derived equation and the proper calculation of A. And you see their perfect correspondence, r squared equals 1, so we're good here. So then I did the exact same thing, but now with the full syn dye. So 4 surfaces and exactly r squared equals 1 for all of these things. So in other words, this can be expanded to more complicated versions of the eye model. We just don't have the equations yet, but we're working on it. It's just, as you can imagine, with these equations, they become complicated at the moment. So to conclude, linear optics is closely linked to Gaussian optics. Of course, there are 2 branches of the same thing, so that was to be expected. We have new interpretations of A and of B. D is still unclear. When we started, Tanya said she really wanted to know D. Well, still kind of unclear what that proportion means, but we're working on it. And the equivalent thickness, it's a new concept. And well, we're still going to dig a bit deeper into that thing. So now the last question is, we need to make this thing ABCD. So A is actual power divides the refractive error. B is the bright new reduced distance idea. C is the combined power, but negative. And D is divide the whole eye power by the vertex power at the corneal plane. So we fixed it.
Thank you very much.
Any questions, traumas?
Trauma.
Yes, I think this is really this. I think this is nice, right? But my main question is why? Why you're spending time doing this? I mean, this is it's a nice intellectual. It's like doing, I don't know, crosswords or puzzles or because I cannot see any utility really. It's just it's nice, but you know, matrix approach is just matrix approach. It simplifies your life. You do the calculation and so on. But what?
So that is a very good question. There are several aspects to it. So first of all, like Tanya said, there are a number of characterizations that you can do of your optical system with ABCD that you cannot really do with ray tracing. I agree, ray tracing is great. You can get, you know, you can do all kinds of calculations that you could never do with ABCD, or maybe you could, but they would become more complicated. So that is absolutely true. It's definitely an intellectual exercise. I agree, but at some point, you know, there are plenty of mathematical constructs that were made just as an intellectual exercise that turn out to be useful later. So in that sense, it was, to me, it was curiosity, honestly. Tanya came to us, she said this thing, it's like, yeah, we don't really understand what they are because, I mean, we have names for these things, we have some rough idea what these things do individually, but you know, once you combine them all and how they interact with each other, that part was not too clear. So that particular aspect could be interesting. Plus, it came out with this reduced distance, and that's, I don't know if it's something useful or not, but maybe it turned out to be something very interesting. Maybe it's just some mathematical construct that will never be used. I don't know. But if no one does the efforts, then
I agree. I just try to make the question a little bit, but I fully agree. But I put it more in the side that is intellectual curiosity, and I'm not completely sure that this is really going a significant practical advantage because we do so nicely with computational ray tracing these days, right? So it's
that is true, but computational ray tracing is like when you solve an integral, you know, by hand, or you just throw it into some kind of computational thing. It's the understanding that counts.
correct. But I don't remember when I did my last integral by hand.
I agree. It's been for me a while as well.
I'm going to backtrack just a little bit on the comment that was made earlier about students that fail, right, and the highest tutorial rate. It's true whether you teach Gaussian optics, ray tracing, or whatever. The students that come in are not well trained in math, and if you want to ask the number of students that eventually get booted or have to repeat a year, it's always because of optics or visual optics and the applications. They just don't have a strong math grip. But I just really appreciated your talk today in the sense of tying the matrix algebra back to Gaussian optics. That made it much clearer for me, and I've suffered with that understanding for years. And that's why I referred all of Bill's papers to Larry. It's like I was having trouble just interpreting it. So I did appreciate it. Yeah.
So then the intellectual exercise was it to make Ray understand it better.
Yeah, definitely.
Yeah, thanks a lot for your interpretation. It helps a lot. But it seemed, if I understand it, you're really talking about Gaussian optics in most of your pictures because you're assuming rotational symmetry. And when we teach optics to beginning optometry students, that's exactly the approach we take. We're talking about Gaussian optics, where it doesn't matter what meridian you're investigating, they're all the same. Where it becomes a little more complicated is when you've got the astigmatic eye. And now you have to pay attention to different meridians because every ray trace to the system is different for every meridian. And your diagram will still work if you're in one of the principal meridians, because the rays will stay in the plane of the diagram. What becomes more complicated for students is when you get outside, it's one of the other meridians that's not a principal meridian, and these rays start becoming skew. They're not in the plane of the diagram, and most people panic at that point if they don't know what to do. So it's that I think the value of jumping from Gaussian optics to linear optics is to help overcome that anxiety. And what do I do with these skew rays now? They're hard to trace. And the simple step along methods that you see in textbooks, they're hard to apply to us. So I think most teachers, they just drop the topic. They only go as far as the Gaussian optics. So I think that's one of the great advantages of their approach, the ability to handle any meridian. And so one of my questions is, does this ABCD matrix vary with meridian? Is that how we should think about it? Or is it just going to pad this matrix out now and just instead of being 2 by 2, it's like 6 by 6 or something, and the same ABCD still applies to every meridian? Can you answer that?
Well, the question that you ask is something that Tanya is wondering. In first, we just keep the system as simple as we can, right? We keep it as simple as we can, but in the next step, Tanya would like to add astigmatism to that. So then each of these ABCD would become 2 by 2. So the whole thing 4 by 4. So if you can handle that, I don't know. We can only know if you try.
So to me, that's the advantage of the ray tracing method. The rays go where they go, because you bring in somebody that's had radial keratocony, and they've got all these. You've got a very irregular pattern all the way around. So we're not talking about orthogonal meridians anymore. We're talking about what happens along any meridian.
Yeah, but ray tracing is a numerical approach. See, they want an analytical approach, and that's a lot harder. You're going to draw me, you're going to create an equation for me that tells me where that ray goes for every ray in the system. It's a lot of work. What do you think, right?
We all have problems. Yeah. Deal with this. Yeah.
I'm just saying that with artificial intelligence, it's not such a complicated problem, although it is complicated, obviously.
So yeah, I mean, this is something I did actually last Christmas. It was my Christmas break project. You know, the university didn't suffer over this. just to make that clear. Any more questions?
Question?
Yes or no? No. Okay. Then it's back to Tanya.
Just to answer Ray's questions, the advantage with linear optics is its ability to handle astigmatism with mismatched meridians and so on. And you end up with a power matrix that's asymmetric, which is telling you exactly about the twist that's happening in the light as it's traversing the system. And our feeling is that, you know, you start understanding your spherical lenses and then you move into astigmatism, and linear optics give you a really, really good understanding of astigmatism. And then you can move on to the higher aberrations. Because if you skip a whole tier of your Zernikes, you're not understanding much.
So, Mike, just say, let me see if I can answer my own question. My question is whether or not the ABCD applies to all meridians. My understanding is that the scalar values of A, B, C, and D of Gaussian optics becomes a matrix. Each one of those A, B, C, and D is now a new 2 by 2 matrix, and so the big matrix becomes much bigger, but it handles all those skew ratios nicely. It's just you've gone from simple scalar values for A, B, C, and D into matrices of A, B, C, and D, which will give Josh something to think about over there. How do you interpret a matrix of A's and a matrix of B values and a matrix of C and D's? And teach me, how do you pronounce say? Can't even pronounce it.
Disjugacy. All right, so I'm going to be building on a topic that Jos introduced, and I think Larry was involved, about scaling the eye. And why would we want to do that? Well, we'd like to be able to facilitate a comparison of the biometric parameters of different eyes, different human eyes, and comparing, for example, different animal eyes or humans to animals. What do we want to do? And we want to be able to see the intraocular distances and refractive powers scale proportionately. Do they scale proportionately with axial length? And Josh showed that scaling works really nicely for emmetropic eyes, but tends to fall over when you start looking at ametropic eyes. So, of course, I had to apply this to linear optics. And so that's exactly what I'm going to be doing. All right, so what do? We start by choosing a scaled axial length. I've chosen 24 millimeters. You can choose whatever works for you. Then we obtain the scaling factor omega such that it's the relationship of the scaled axial length over the axial length of that particular eye. All lengths need to be scaled by omega. So any lengths are scaled by multiplication. Radii of curvature are scaled by the same scale factor, but when you convert to power, it becomes a 1 over the scaling factor. And so, for example, the scaled power of a thin lens simplifies to 1 over omega and the power of the thin lens. So it all kind of fits very nicely. If we look at the linear optics, we have the transference of the scaled homogeneous gap, and so we multiply reduced distance by omega, and the transference of a scaled power is simply 1 over omega times the minus f. And then we start multiplying out, and you can see it gets pretty messy quite quickly. So we've got a or a two-surface eye with 4 matrices, transferences, reduced distances, and powers. And this is what the ABCD look like. So D is pretty simple. C we are expecting to be negative over the power of a thick lens. B has lots of reduced distances and only the power of the lens. And A includes all 4 parameters, both lens power, corneal power, reduced distances. And so that's just what it looks like. And then we scale it. So we've got scaling factors in throughout and multiply out. And this is what we obtain. So A doesn't change. There's no scaling happening there because any scaling is cancelled out, omega over omega. So you can see each time it's being cancelled out. Similarly for D. So D, A and D are not scaled. They're not affected by the scaling factor. B, this is B over here times the scaling factor, and thick lens power 1 over scaling factor. And so our scaled transference looks like this. A and D not affected, omega 1 over omega. Let's check for symplecticity. If we obtain the determinant, you can see that the 2 omegas are going to be cancelled out, and we're still going to get 1. And so we are happy that this is still a symplectic matrix. and obeys all the rules that we needed to obey. Okay, so let's generalize astigmatic systems. This was Larry's question too. So we know that the 2x2 Gaussian transference becomes a 4x4 transference, and each element is then represented by a 2x2 submatrix. The scaling factor, however, is still scalar because we're scaling the axial length, which is a scalar value. So we can make the scaled axial length, let's fix it to 24 millimeters. As per the Gaussian system, all the gaps are scaled by a scalar value, so it's going to look like that. And all the toric refracting surfaces, we have two powers, each of them is scaled. And so if we scale meridian 1 and meridian 2, what is happening? Well, the power matrix is simply scaled by 1 over omega, and we have our scaled power as well. Okay, so let's play with this. Let's check this. If we have two juxtaposed optical systems with astigmatic elements and 2x2 submatrices in them, we multiply in reverse and we get something that looks a little bit messy like that. We'll just call it ABCD. Now, if we multiply the two scaled transferences, so we scale B and we scale C, and the same for the first one, multiply them together, we're getting the same A, the same D. This is simply scaled by omega, because it's the same there, and that by 1 over omega. And so we're happy that no matter how many components and elementary systems we have within our optical system, we can take the transference of that system and simply multiply B by our scaling factor and multiply C by 1 over our scaling factor. And so the scaling of a transference becomes very, very simple. Okay, so, I already said that. Okay, so what are the implications? Let's have a look at the derived properties. And here is a summary. So power, this is the relationship. And when we get the scaled power, it's very simply 1 over omega times C. The refractive compensation, we know that A doesn't get scaled, only B. And so we get omega times B inverse times A, or 1 over omega times the original refractive error. We continue back vertex power. There we can see what's happening with C. Front vertex power will look like that. Incident cardinal points. You simply need to scale the position of each cardinal point by omega. And the same for the emergent cardinal points, simplifies to this. Larry's power vector, exactly the same. It's going to be 1 over omega times the power vector, and the thick lens power will simplify to this. So we don't need to calculate each of those derived properties separately. We can scale it appropriately and obtain our scaled factor. Let's look at an example. So here we have a 4-surface eye. We have the two front and back corneal curvatures, radii curvatures, sorry. Same for the lens and our various distances. If we take the axial length of 25.85 and we scale it down to 24, our scaling factor is 0.9286. So it's a little bit of a scale. Okay. Here is the transference of the original eye. Here is the scaled transference. So A and D stay the same. B is a little bit shorter, and C goes from -60 to -65. Okay, so there's a bit of scaling going on there. Our corneal plane refractive error is minus 4.55. And if we take the scaled A over scaled B, we get minus 4.9. And if we take this refractive error, this one, and divide by our scaling factor, we get the same value. So that is how the scaling will relate to each other. All right, so to conclude, using linear optics, it's a very simple task to obtain the transference of a scaled eye or a scaled system. We simply weigh B and C with our scaling factors. And in addition to the transference, we do need to know the axial length of the original system, and it's only B and C that are affected, A and D not affected. Any questions? Well, you either all understand it perfectly or you're all bamboozled.
I'm just still trying to get why would we scale, or if we scale between the two?
So, for example, if we have two eyes with different axial lengths, but they're both emmetropic, how do we compare the two and see, is it simply an eye that's bigger in all dimensions, or are there other factors within the eye that are allowing that eye to be emmetropic? So if you scale either the bigger eye or the smaller eye so that they both have the same axial length, then you are going to be able to compare and see what's happening with those internal structures. Okay. Any other questions? No?
Okay, let's take a break first. How long? 15 minutes? Or 10 minutes? Yes, 10 is enough? Okay, yeah. In 10 minutes.
Coffee break now.
Yeah, going.
Time for some coffee. Yes. So. What you want to analytical way? Yeah, I know.
He's doing it.
As long as we get cycle, and
It's not that difficult. They just holy. There's so easy. Everything. And anyone who teaches them like
but I'm talking more generic. Any set of formulas. Because we have all these different shapes. So it's best just to get enough information about the weights, that's the shape, right? Then yeah. That's not.
It's just, what's the model of the architecture?
But it's different sizes.
Yeah. Control all the color faces, so you compare them. No, it's just.
That,
it's a different
that,
color.
yeah,
So it's gonna be really different.
yeah, that could, that could be. Yeah.
Good job.
Oh, he is wonderful. I
Finally,
I can.
I've been stuck on this thing for 30 years, you know.
I have a unique perspective.
Because I'm the hero, because he never wanted to interpret. He said, why interpret? This is just for me out. It's just me out. Time to interpret it.
Thank you. Oh, good. No more? It doesn't stop anymore? Well, I'm glad you were. Otherwise, I would have been in a
Spot. Darf ich rausmachen? Okay.
Hey, everything's good? Yeah, I'm glad you do. That's it. You're in shape.
I'm alive.
I heard that you weren't feeling well.
Okay, let's do it.
It's not.
Last year, I had they detected me. It's prostate cancer.
Oh, wow.
It's they get a minor surgery. It's very early. And since that, they basically forget.
Oh, good.
You
never know.
I so this was very early stage.
Where is the spot?
You can do the full face.
Yes. Okay.
Yeah.
It's kind of risky. You can do nothing, but it's like never done.
Yeah, right.
Then it's like a new therapy. They are very good on this. Yeah, and this is what I get. Was a little bit uncomfortable for actors after this. This is very high voltage.
Are you trying to do it?
And then, then later it was more than probably like 2 months. A little bit like, but
That's good.
That's what he was
then
saying.
I try to forget it. Well, double check.
I was like up by 7 and I was like, all right, I want to sleep a bit. No, so I was awake like 6:30. So I went through my and then before I take a shower. Well,
So you're thinking about that?
I don't know. I thought it's usually a stand, right? Some reason we do this
Yeah.
spot here and like studying. I was here 9, 4 and 5ish. Just calming myself down. But yeah, really everybody starts elastically. But then it's new place and we're not that You might go as in you would president or no, I'm saying you president. Or just president next and afterwards me. Okay, where's PB? There's PB, there's Sylvia. Oh, okay. And this. I will. Actually, to see if you don't want to sit here and institution, okay? Sure. Like I told you, I can give you a personal presentation afterwards. I can give you a personal presentation afterwards. But yeah, if you're staying, would you like a picture of the presentation? Something that makes me become serious individual. I'm very serious, you know. Well, let's show Phoebe that we are serious researchers.
And they looked at me exactly.
Do you? That gray and blue band, it's really nice.
Yeah.
I was like noticing your it's Thank you. I'm in my usual conference outfit. You might have seen this on TV 3 times, so I'm not going to ask.
It's nice actually.
I like to repeat it.
You always like to promote nice.
Hope so.
I like
So right now, Camille.
I really hope I don't drop the mic. I really hope I don't drop the mic.
You don't.
Yes. This is very embarrassing. I don't like holding a mic and talking. I probably feel like singing.
Yeah. Yeah, no, Brian and Bethany had to get back because Bethany's parents were keeping their kids. And they're over, and it's like 2 weeks. You're gonna be back in 2 weeks. So we did. Oh, no, we were. We had here almost. Not here. We did the garden first. Right up there, which is beautiful. You should do it sometime. Oh, really?
So you got the USB.
Yeah, I took Jos as the USB.
Oh, good.
I can't remember
her voice. Isabel.
What is it? I should eat something.
I like it. I mean, that gives you. We don't pay attention to time. So tiny. And I like the practical implications, but I also. Yeah, it's just. Because Josh did help me a lot. He's alive. Yeah, he's still alive. He was going to come, but you know, so. I know.
When
I know.
how clear it is.
I'm sitting there going, you're ahead of me. I know.
The pictures you take here,
But the problem I have
page of
is I want to student stuff.
Oh, as in,
yeah, I can understand.
yeah, no, I think we're fine with that. It's fine. I just want to know where they are so I can check them out. Okay.
But so this afternoon for stable days. So.
Bengitsho uzobonakala ukuthi how clear it is.
Yeah.
Like ezinye bed that we were watching were not that clear. So
Yep, that was my bias. Yeah. This is going well. Yeah. I'm sorry.
Let's get a coffee cup.
Exactly.
Next year, matrices.
You're right. It's been a little boil or something. With his eyes, so it makes sense to see them get funny. And it's a tiny bit or in a way, probably it's also right. That's it. Then yes, we have better. Recreate anything, you don't understand it. Does wonders, but something comes out. That's what it is. You'll probably be the reviewer once it comes out. Probably then it's up to the reviewer. The other people can review it.
The database that you sent me, this was a whole bunch. I appreciate you doing it.
No problem. No problem. You're retired. You're retired.
Like I went full time.
Sorry.
So I get my name on there. You took too far.
Okay, let's start the next session. I was supposed to be the last of the previous session, but things ran out a bit. So now I'm just the first of the next session. And the session is about scaling, well, the session, my talk is about scaling vertebrate eyes and their dioptric structures. So it connects to what Tanya has been saying just now. So Tanya was looking at more general in human eyes. I will be looking at, well, pretty much any animal eye I could get my hand on. Little spoiler alert, there were quite a few. So as Tanya said, and Ray mentioned it, and well, a lot of people said it, eyes come in many different sizes. And well, that's hardly a realization. If you do the clinic, you know, You see that all the time. But I tried to apply this to animal eyes, and this was a bit inspired by something that Ray said to me, maybe VPO Antwerp 2016. He said two things. The first one was that a mouse eye and an elephant eye, they can both see sharply, which is something obvious, but connecting that kind of said, well, human eye is somewhere in between there, and there should be some kind of link between all of that. And another thing he said was that the future lied in big databases. But there is no big database with the kind of biometry that I need. So I decided to build one based on the literature. In fact, I built two. The first one is on human eyes, and that was published 2 years ago in a big paper, data for 300,000 eyes or something like that. But the second one is not published, and this is the first time I will present that. So, and this is about animal eyes. So starting from the realization, eyes come in many different sizes. Well, these are human eyes. These are human ametropic eyes in the whole range that they can be found between 21 millimeters and 26 millimeters. Now that doesn't seem like a big range if you do it between your fingers, but optically that is a range of about 18 diopters in actual power. So that's enormous. You cannot just jump from one to the other. This is something that has to happen in a growth process, right? It has to be in a very slow growth process, and the cornea and the lens need to adapt to that particular axial length. Otherwise, ametropia is impossible. And this is part of a paper that came out just last May. So you can look it up. It's in Opia. So everything I just said about human eyes is also true for animal eyes. And animal eyes come in many, many, many different sizes. So the older ones in the audience might remember something from the 1970s, which was called scales of 10. So it started with a picture of an atom, and then it zoomed out and 10 times larger, 10 times larger, until you had the whole universe. So I wanted to do that with the eye. So the smallest eye that exists, well, it's hardly an eye, it's this thing here. So it's that little red dot. That little red dot here, that's a photosensitive pigment in these little single-celled organisms, and they have a little tail, as you can see here, so they can swim towards the light, because all this green stuff is chlorophyll. It's an animal with a bit of plant inside, so they like light. But these things are really tiny. The smallest, well, big word for what it is, but the smallest eye is about 3 microns. Then 10 times larger, we end up with this thing. It's called a chiton. It's something that lives at the bottom of the ocean, and you don't see any eyes. That is because they're microscopically small, and he has hundreds of them. And they look like this. So it's already a bit like an eye, like we recognize it. It's actually crystalline shell material. And this thing is a lens made from the exact same material, except that the exact same material here really is crystalline. So this crystalline lens really is a crystal. So I thought that was pretty cool. And it has something like a cornea. I couldn't really distinguish on the image what was the difference between cornea and lens. So the smallest creature that has an eye that we would recognize as an eye is this thing here, which is called a blind snake. It's a blind snake because, well, it has a tiny little eye. All these structures are so small, it cannot function. And the second aspect of it is that, well, it's a snake, it has scales, and in this case, the eye is covered by scales. So it's not going to see all that much. Maybe it has a bit of light perception or something like that. But being a snake, it has a whole lot of other senses, so it probably won't really miss it. So the first animal we would recognize is a mouse. And a mouse has an eye about 3 millimeters. And this is an eye that we can recognize as being an eye. It's used in experiments. It looks something like this. So even though it has the elements that we recognize, it has a cornea, it has a lens, but this lens is so dominant, right? It's almost spherical. It dominates the entire eye. And then if you go bigger, 10 times bigger, we go past humans, we end up with owls. An owl has an eye of 30 millimeters, but the shape of the eye is quite a bit different. In fact, a lot of bird eyes, if you look at them, they look more like an LED shape, like a little tubular thing with a round thing, and then this little fin at the end for some reason. So that's probably what fits best into a bird's head. One little fun thing, some of you might know, others don't, is that they have a very impressive stability of their head. So if you turn the head, if you turn an owl like this, it has this wonderful ability to keep it. It has a built-in gyroscope. So, you know, maybe if you want to have a drone or something like that, maybe you should consider one of these. So what is the largest eye out there? Is anyone familiar with the largest eye in existence at this moment? Huh?
The whale.
The whale. It's coming close. The giant squid, exactly, this one. It ranges between a soccer ball and a small beach ball. So something that size. Now, something that size is incredibly heavy. A sphere of water of 30 centimeter diameter is somewhere between around 11 kilo, and in pounds it's about double that. It's pretty big, but it's especially impressive. It's in structure, it's very similar to our eyes. It has a cornea, it has a lens, except it doesn't have one lens, it has two. Now, why does it have two lenses? This is an example of convergent evolution. Convergent evolution means in totally different branches of the evolutionary tree, the same thing appeared twice. So the mollusks, of which the squid is a part, they deviated from our branch about 500 million years ago. And at that time, our branch did not have eyes yet, and their branch didn't have either. And in both cases, they developed something very similar. So the system that we have is apparently so beneficial that the same solution was reached at least twice. Now, this is, of course, not a vertebrate, and vertebrate is in the title. So the biggest vertebrate eye was that of an ophthalmosaurus. So the name already says it. It's an ichthyosaurus, a fish-like dinosaur with an eye of about 25 centimeters. So a small soccer ball. But these are extinct, of course. So putting all these eyes on top of each other, and well, it says Sicilian here, but actually it's more like my laser dot for that blind snake. You see that there's an enormous range, all on the same scale, photosensitive structures in 6 orders of magnitude, eyes that we would recognize in vertebrates in about 4 orders of magnitude. The smallest order, it's not very functional, but in this giant squid, definitely very large. When it comes to whale, the whales are here. So the whale can go about 10 centimeters. So good 4 inches. So we have all these eyes with very similar structures. I hope you can recognize the human eye. Which color is human? Yellow. Yes, exactly. So they all look different, but somehow these bilenticular optical structures, they essentially are the same. So if you would recommend, if you would create them as an eye model, it would be pretty much the same structure. You have a cornea, you have a lens, you have some distance in between, and a retina. That particular aspect remains constant in all these things, no matter what they do. Even at one, the 4-eyed fish, that's a favorite. It has actually 2 different parts of the cornea, one for above water, one for underwater. So they can see prey down there, but they can see for predators above water if there's a bird or something like that. So it's a pretty, it's called anableps. You can look it up. It's a pretty cool eye. So this is where I start with the biometric variations. And the thing that Ray said back then is like, we need to have big databases, and also, you know, animals of different size can all see very well. So I went into the literature, and in the literature, there are literally hundreds and hundreds of papers, and there were books, and some people were pretty obsessed with animal eyes. So that's good for me, and I don't have to dig as deep. So these are some of the people that published books with hundreds of eyes, especially this guy here, Britland. He never published anything except for his PhD thesis in the 1980s. That was apparently possible. And he had literally over 1,000 different vertebrate species in there. He had dissections. It was a thesis of 2,000 pages, literally 2,000 pages, of which 1,900 were either diagrams that he drew by hand or just tables, lots and lots and lots of tables. So I imported all of that. Great. Thanks to Ray, actually, he downloaded it from me back then. It's an enormous thesis. So in total, I had this many records of this many species, 1,914 species, and I had enough information for 114 species to make a four surface eye model. So how did I get the lens information? Well, in a number of cases, I did get a cross section. So I get a cross section, and then with just something like image J, you can follow the curvatures of the different surfaces. Now, any model requires assumptions. There is no escaping that. So first of all, the refractive indices of the cornea and of the humors, I just assumed that they would all be the same. There was some information in different eye models and different measurements that seemed to kind of confirm that assumption. So when it comes to cornea and humors, no problem. I'm not talking about the lens. That's a special case. It's a special case because I used it as a free parameter to balance out all the different parts. A more important limitation is, well, all these animals or all this material was post-mortem. So yeah, you can't really put an IOL master in front of an elephant or something like that. That's not going to end very well. So I just assumed that these post-mortem data represented in vivo data. And everything targets emetropia. And okay, there's some reports saying that small animals tend to be more hypermetropic and so on and so on. These are small eye artifacts. It's called a small eye artifact. It's just that the thickness of the retina tends to become, they're pretty much uniform across species, but a 0.3 thickness is, of course, much more important in a mouse than it is in an elephant, right? So that's where that short eye artifact appears. So let's do some allometry. That's just a different word for looking at proportions of things. So we look at the animal mass. I could look at the animal height or length or anything, but as you can imagine, if you just look around in the park here, you see, you know, zebras that are kind of like boxy shape, but you have an elephant that is a large box, and then you have a snake that is just a really long little box, and you have a giraffe that is a very tall box. So it's much easier to work with mass, just to get a sense of scale. And on the other side, we have the eye globe size. So these are thousands of little dots organized according to the branch of the tree of life. So we have fish, amphibians, reptiles, birds, mammals, and humans, a special little box right there. So so the humans is pretty okay. Somewhere in the middle here, okay, we got all the really small creatures right there, and I only now realized that this looks like a shrimp. So when it comes to this, it's a power law that is already known in fish data and in different scale data. If you have animals of different sizes, seems to be some kind of power law. So that power law extends to all species that we could find. Now, let's look at this just single logarithmic. So only the animal mass was scaled here. So this is a globe size. And then you can see here all these enormous eyes. They're all aquatic species. So the blue dots are aquatic species. And that makes sense. Like I said, the giant squid has eyes that are about 10 kilos of weight. You know, if you need to carry 2 of those in your heads, you better be very buoyant to deal with that. So when it comes to scaling of the eye, so we have the axial length and the anterior radius of curvature of the cornea. And you see, again, there seems to be some kind of power law going on, luckily, otherwise these creatures would be either very hypermetropic or myopic. Lens thickness as well, and corneal diameter. The humans are located here. When it comes to the corneal radius of curvature, it's kind of where most mammals seem to be. But when it comes to the lens thickness, it seems to be on the thinner side compared to all the others. When it comes to corneal diameter, it seems to be on the spot. It seems to be more or less a power rule. So if you have a double logarithmic graph and you have a linear relationship, that's a power law that seems to work, except here for lens thickness, some of the smallest animals, there seems to be something strange going on that I haven't really figured out just yet. Now, we can take these animals, these animal eyes, and we can scale them, just like Tanya was scaling them earlier. So this time, and this should also answer part of your question, Savani. What can you do if you want to compare eyes of different size? Well, you just, in this case, you divide by the actual length. And then you can see, you can call the 0%, you call the anterior surface of the cornea. The black dots are where the posterior surface is. The red one is the anterior lens, and here the blue is the posterior lens. And if you look at that, then you see that humans seem to work pretty well when it comes to the anterior chamber, but when it comes to the posterior surface of the lens, there it seems like it's much more forward than in any of the other species. There are a couple of others, but overall humans seem to be quite unique compared to all the others. And if you remember, I used the lens equivalent refractive index as a free parameter to balance out the whole model. Then you see that the lens index is quite low in humans compared to all the other species. So if you look at the cross-section, if you actually look at the actual data, you will see that in many cases, these eyes have very, very spherical, or much more spherical than humans, that the crystalline lens is really thick, very, very round. And you'll see that even in giraffes, which have pretty large eyes, actually, something like 6 centimeters. Also in elephants, actually, giraffes have bigger eyes than elephants. And horses as well. But humans and closely related primates like chimps and gorillas, they tend to have much thinner eyes. And my theory, I don't know, I haven't really checked it in the literature, but I think it has something to do with accommodation. To us, accommodation is probably more important than many other animals in nature. So if you remember one of the first slides, I showed you this little animation of how the different elements of the eye change for emmetropes of different sizes, right? Human emmetropes of different sizes. So that's what these solid lines represent. And then the dashed lines are regressions from the previous slide. So the previous slide where I showed you these scatter clouds, the linear relationships are shown here by the dotted lines. And overall, human eyes seem to scale pretty well according to how animal eyes in nature seem to scale, except, again, the posterior lens thickness. So we can look at the different refractive contributions. So like I was saying a couple of days ago about the pseudo eye, so there is an importance in the balance between the corneal contribution to the refraction of the eye and the lenticular one. And the red ones are the lenticular contributions, the black ones are the corneal contributions. And you see in most species, it's the lens that is dominant. And the cornea seems to be of lesser importance when it comes to providing refractive power, except in humans. Probably a couple of other species, but especially in humans in this case. So there seems to be an important difference. You also see that there's a bunch with negative corneal power. Those are fish. So if you have a radius of curvature anteriorly and posteriorly, but the posterior radius of curvature is a bit smaller than the anterior one, and you're underwater, then the net result is a negative power for the cornea. And then there is one other special one here, the chameleon. I found 2 papers confirming it, but for some reason it seems to have a negatively powered lens by about 20 diopters. So that's a bit of an outlier there, but I did find some multiple references about that. So I guess it has some value to it. So to summarize, bilenticular eyes can exist on many scales, and the optics scale along with it. Luckily, that's how they accomplish emmetropia. It's predominantly lenticular in most species, but humans seem to be a bit different from that. So in small and aquatic eyes, it's also mostly lenticular. Larger eyes tend to be a little bit more mixed. Human eyes have thinner lenses, deviate from all the others, and it's a work in progress. So this is the first time I present any of this to anyone. It just seemed like the right place, right here in an animal park to present this. So, thank you very much. Any questions?
Thank you for a nice presentation. Did you exclude the animals who are known to be myopic, let's say like porcine eyes are known to be?
No, I made the assumption that every animal eye was emmetropic, because there's also then the question is, in what way was that measured? Was it really properly measured, properly refractioned, this animal eye?
Yeah, but fixed eyes, as I know, fixed eyes are myopic because of the distance which pigs needs to have. Yeah, because they usually just look on this distance, not far.
Yeah.
Yeah, so that's, I think they may have different relations of the eye parameters.
Yeah. Yes, well, like I said, I assumed emmetropia for all of them, just for simplicity. I don't think it would have changed all that much.
Yeah.
But how much is it, if you could tell me?
You mean the refractive error? I'm not sure now, but I think it's about 5 diopters, something like that.
Yeah. That would probably not change all that much. So, but yeah, I'll look into that. Any more questions?
Oh,
no. Okay, then the next person is going to be Sharon, who is going to present. Let's see if I can find her presentation. It's already open. So she will talk about the Wavefront-Guided IOL correction for keratoconic eyes.
Hi, everyone. Before getting into the topic of my presentation, I would like to do a small look into the background. So the study, it's mainly focused on two eye diseases. First one is a bit more common disease, cataract, where the crystalline lens of the eye becomes more cloudy, mostly due to aging. That the crystalline lens, need to be replaced by an artificial lens called intraocular lens. The next condition is called keratoconus. Keratoconus, where the cornea gets progressively goes through a progressive thinning and bulges out, that the eye would have a lot of aberrations like irregular stigmatism, coma, spherical aberration, and several high order aberrations. So the study is about what happens when these two diseases happens in one eye, both cataract and keratoconus. So cataract patients with regular refractive errors, moving the changing the IOL and getting like a clear vision is easy, but with keratoconic patients, when they have a really bad cornea, this could be a bit more difficult. There are a lot of studies that suggest that toric IOLs can adequately correct for keratoconic eyes, but this is true for mild keratoconus. When the patients have like a moderate to severe cases of keratoconus, it's not easy to correct it with toric IOLs. They often need RGP contact lenses, rigid gas permeable contact lenses after their surgery. So this came to the thought of having a bit more customized correction or a wavefront guided corrections for the keratoconic eyes in the IOL plane. So the wavefront correction, that's the wavefront optimization algorithm we used in the study. It's from this paper where the eye is the whole eye on a
ray tracing platform. It's ray traced with the best toric RGB contact lens correction. And the wavefront is calculated by the Zernike polynomials. And from 2 to 8 orders of Zernike polynomials, picking an order, we take the Zernike polynomials, multiply it with the refractive index of the contact lens correction, and reduce it, like subtract it from the anterior surface of the contact lens. So this is how then the surface will be changing. The wavefront would through multiple iteration. This process is repeated through multiple iteration, and this is how the anterior surface of here I show the example of IOLs, but in the this paper when the contact lens would change such that the wavefront now has very minimal aberrations or no aberrations in some cases. So how this project was done? Methods. As first, we need a set of eyes. The eyes used in the study is generated from a statistical eye model, which gives all the biometries that and the topographies required to optically simulate the eye in any ray tracing platform. We use a custom MATLAB ray tracing platform, and we ray trace the eyes at 555 nanometer and calculate the wavefront in 5 millimeter pupil. That's and the IOL used in the study. So we used bag in the lens IOL, not the regular lens in the back IOL. So bag in the lens IOL, it's implanted in such a way that the circular opening is made on both the anterior and the posterior capsules of the lens bag, and the haptics of the lens is fit in such a way that the lens is sandwiched between the anterior and the posterior capsules. So this means lesser chances of movement, which is very important when when you're doing a wavefront-guided collections, because they are very sensitive to the movement. So we pick this IOL when there's less chances of movement, and then on this Syndice platform, this is a theoretical paper. We did completely in a theoretical platform. So we put the IOL and scan through different powers until we get the best spherical power for the IOL, and the anterior surface was changed accordingly, as I shown in the wavefront optimization algorithm, and the surface was changed. So this is an example of what happened. So what's the result? You can see with uncorrected, it's very poor VSX. So VSX is a metric we use, visual strength ratio, to understand the image quality of the eye. So you can see with uncorrected or with the toric IOL, it's only a slight improvement of the VSX. But with fourth order correction or fifth order correction, the wavefront is getting better and the VSX is improving. And towards the eighth order, it's already reaching a very impressive 0.966 VSX. So maximum VSX is 1. So that's already very close to perfection. So this process, this was repeated for 20 keratoconic eyes. And this is how it is. We went from 2 to 8 orders. I skipped few orders that are like intermediate, but this is pretty much what is happening. By fifth order, already the eye is reaching the upper bound. The dashed lines are the upper bound, mean, and not lower bound VSX values for normal eyes. So the keratoconic eyes with the fifth order correction, it's already reaching upper bound. So it's not always uniform for each eye, depends on the eye, the correction changes. So fifth order is already adequately correcting for a keratoconic eye, and by sixth or eighth order, it's already reaching closer to 1. That's all good. But what happens if there's some misalignment? Like I said earlier, in bag in the lens IOLs, misalignment chances are lower, but it's not absent. The IOL would shift horizontally, vertically, or could rotate. So let's see what would happen with such corrections when such misalignments could happen to the wavefront correction. So this is when there's a decentration. Let it be an X or Y decentration. This is just an example of keratoconic center 15. The decentrations and the shifting VSX, it changes depending on the correction or depending on the eye. I just picked this eye because it kind of agrees with how it's changing in most cases. So with X and Y decentrations, you can see by 0.2 millimeter shift itself, it's already reaching closer to the lower bound. So for bag in the lens IOL, the shifts are 0.1 to 0.2 millimeter shift could happen according to all the papers I read. So already then the VSX is shifting, and that's only for fifth order. And for eighth order, that shift would be much more higher. Like it's already from 0.1, it could really shift that much. So what happens with this shift? It's with horizontal movement. For this particular eye, I looked into each aberrations and what really happens. You can see in the center, it's like without any change, where there's like not any defocus, how the like where there's no change, when it shifts a little bit on the like 1 millimeter left or right, how aberrations that were not present could happen. This is a problem when you will move a bit. And same thing, not exactly the same thing, but a different thing will happen with when the lens moves in y direction. So these changes in aberrations, it will depend according to the each correction. And I just checked what would happen if the lens, moves front and back and optical axis like in shift in z direction. This is not really possible for back in the lens IOLs because they are mostly stable, but could happen with a regular lens. And yeah, this is what would happen with any lens, I think, when it moves shift up and down. That's like a defocus would change. Not other any different corrections, same thing was seen. And now then what would happen with the rotation? So back in the lens, IOLs have I think like 3 degrees up to 0 to 3 degrees of rotations in average. So this is why of the V6 shifts for 4th to 8th orders. You can see 4th order, it doesn't improve the VSX that much, but then the VSX also, the shift is not that much varying. Even there's like a case where the VSX is a little bit more higher than when it was in 0 position. But yeah, when it goes from 5th, 6th, and 8th, the VSX shift is very low. Like I think by 2 to 3 degrees, it's already reaching the lower bound VSX for normal eyes. This is what happens with the rotation and how the other vibrations like vertical trefoil, oblique trefoil, and all happens with the shift in degrees. So to conclude, wavefront-guided corrections in back in the lens IOLs are capable of significantly enhancing the visual acuity of the eyes in keratoconic eyes, and the 8th order could almost reach near perfect optical performance. However, they are very sensitive to shift. After post-surgery, when the last light shifts, the change in visual acuity is also very big, which is a bit of a risk because this is an invasive procedure. It's done to cataract surgery, so post shift that it's a bit of a limitation of this correction. And that's all. Thank you. Any questions?
Thank you so much. That was a very nice presentation. I enjoyed it. So I just have a question. So in the case of a cataract with keratoconus, so because the goal of going for cataract surgery is to get improved optical quality, right? So in cases where somebody goes for cataract surgery, maybe it's unsuccessful, can you still continue with the correction or it's an exception? So cataract surgery was not successful, so it wasn't done nice. The optical quality is not so great. Can you still continue with that correction or it's an exception?
I'm actually an optical engineer, so I'm not really good with the clinical things. So I think it's a bit more surgical question. If they could surgically put another lens, yeah, they could still put the corrections there accordingly. But again, I forgot to mention this is completely theoretical. To do it practically, it's a bit more impossible. Not impossible. I guess there still need to be a bit more technology because I'm already putting the best spherical correction lens on there and then getting the wavefront and then calculating. Which getting the wavefront after the lens was placed and then putting the correction. This is not really something we could do in actual surgical scenario. So it's a bit of a freedom we could do with theoretical simulations.
Thank you for the presentation. Just to follow up on the question, I'm not sure if if you're correcting someone with keratoconus, do you take them, because usually if someone is keratoconic, they are more myopic. So do you take that into consideration or you just put the power of that lens, then you correct the keratoconus later on. Thank you.
So how I did this was like the IOL and I keep changing the power, the different kinds of IOLs there until I could get a good visual strength ratio. So yeah, it just changes accordingly.
Thank you. Yes, sir, a practical turn. Maybe there are intraocular lenses that they have a small aperture, so they are usually intended for getting a little bit of depth of focus, right? But in several clinicians they use these intraocular lenses with a small aperture. So they are basically black outside, and they have a area of 1.5 millimeters, something like this. They are using these for keratoconic eyes, and of course the reason is that's basically blocking the peripheral arteries. So that's something that you would be very easy to incorporate in your model just by playing also with the pupil size, and just this is the trivial way to do it, right?
Thank you for that question. Actually, it was actually my first project that I did, not really with the wavefront corrections. That one was mostly targeted for the RGB contact lenses. After the lens was fit, we ray trace the whole light, and whatever the lights that are out of the point focus and causing an aberrations, we block that in the contact lens plane. It's more like we kept a virtual pinhole in the retinal plane, and whatever that goes out, we block it. So we get something like an irregular pupil. And this can be put into like ion plane or anything. I just did it with the contact lens plane.
Yeah, that's what the other option, right?
Yeah.
Corneal inlays, that's another possibility.
The first paper, it's already published that with the contact lens plane.
You are doing cataract, you go with
Intraocular lens as well. And it's more stable if it's put into it. Thank you. Any other questions? Good.
So the next presentation is by Professor Larry Applegate, or sometimes known as Dr. Roy Applegate. This is the density crisis. Okay, so Ray Applegate is going to tell us about aberrated eyes and wavefront error. So thank you.
Okay, so for the last almost 25 years, we've been working towards making it practical to actually fit wavefront-guided contact lenses on highly aberrated eyes in the population. And it's beginning to go that way. Not only our lab, but other labs have done it, and it's becoming commercialized. And so I'm going to just show you some of our early data that was done in-house, and then compare it to what we actually achieved with clinicians that weren't trained necessarily like the in-house people. All right. I am a consultant for Wavefront Dynamics, and as is Jason Marzak, my former graduate student, now faculty member, and then people from Wavefront Dynamics, and then Christina Sent, who used the platform, developed the platform of the contact lens called the iPrint lens, and I'll talk a little bit about why we chose that. Okay, so spherical corrections often do not meet the needs of the patients with highly aberrated eyes, regardless of the cause, from keratoconus, pellucid marginal degeneration, trauma, bad refractive surgery outcome. All kinds of things make these eyes subnormal. And to give you an idea with some simulations, if you take an eye, no eye is perfect, but I'll use that as a reference. Then low normal aberrations, we all have blurry images on our retina, high normal aberrations, and then the highly aberrated eye. And all these eyes have best spheral cylindrical. Right? So we all see a little differently, right? And we all get very used to how we see. So we have a wonderful image processor above that. If the image is stable, we learn how to interpret it. But a better image gives you more information, right? All right. So wavefront-guided lenses are becoming much more popular. Still relatively limited, but these are some of the groups that have actually reported on in the real world. Few optometry programs and even fewer ophthalmology programs really teach wavefront optics. And the reason this is important, we can do linear optics or matrix optics, right? But it doesn't account for the actual weird shapes the optics have. There's a bunch of assumptions with them. And so we eliminate those assumptions by actually measuring the wavefront error. And there's a lot of problems that come up with wavefront sensing. We tried to talk about them, Larry and I, yesterday, give you some insights. You need to understand how the instruments work. Okay, so wavefront corrections, unlike spherical cylinder corrections, have to remain relatively aligned, or quite closely aligned, actually, with the underlying wavefront error, because you're correcting each local area with a correction. And if you move that correction to another part, it's not going to work. Okay, so consequently, movement of the wavefront-guided correction with respect to the underlying wavefront error induces marked variations in image quality. And if those movements are large enough, you can actually make the image worse. Right? So you have to have a stable platform. And that brings me to the iPrint scleral lens. The iPrint scleral lens actually uses a mold of the front surface of the eye, right? And then that mold is scanned, and the design of the back surface is based on that scan. Okay. And the reason that's important is that the lens is much larger than the cornea, 18 millimeters, right? Sits out on the conjunctiva over the sclera, and the sclera is irregularly shaped. So once you make a form that conforms to the shape of the sclera and the cornea, then that lens is very stable. And they turn out to be incredibly stable, much stabler than 0.2 millimeters, and rotation is quite stable. You can use just a large scleral lens. A lot of people are doing that. Scleral lenses by nature are relatively stable, but the advantage of the iPrint platform, you put it on and it finds the location. So you can put it on upside down, you can put it on sideways, and it will rotate to the right position. And that's a real advantage. Okay, so the tolerance was talked about by Sharon just a moment ago. We published a paper on that for correctly made wavefront guided corrections to misalignment scales with the magnitude. The more complex you're trying to correct, think of a military person that encountered a bomb, stepped on something, they were inside of a vehicle, and their eye got all lacerated, sewn together. It's very irregular. So you have to, the more complex, the more stable the lens has to be. For a moderate keratoconic eye, to keep vision stable, moderate to severe actually, we're talking about a movement of around 0.2 millimeters plus or minus, and a rotation of about 5 degrees, less than 5 degrees. Okay, so instrumentation requirements for efficient clinical use of wavefront guided corrections. I went over these yesterday, so I'll just state them briefly again. You need a high enough density wavefront sensor to be able to detect all the variations. Right? If you undersample, then you're not going to have enough. We're using a very high density wavefront sensor. So about 2,065 samples over 6 millimeter people. Dynamic wavefront sensing for several reasons. We discussed a little bit yesterday, from like tear film dynamics to little movements of the contact lens when it's on the eye and stuff like that. You need to be able to measure the wavefront over time, average, and determine the best wavefront guided correction. You also have to have something in the instrument that will monitor whether the contact lens was in fact stable. If you don't have a stable platform, there's no reason to proceed. So you need some kind of dynamic motion detection, and some kind of lens that has a mark on it that can actually be followed and analyzed automatically. And you need to display the fundamental data. I said yesterday, we're working on algorithms that detect good images from bad images, but they're not perfected. I always advise anybody to look at the spot diagram to see if you believe it. And then display information, because as it goes into clinical practice, you need to be able to turn it over to technicians, and the technicians love to be guided. And at least in our clinic, and I assume other clinics, they're famous for taking shortcuts if they can, and they'll do it. And so you have to have a sense when you look at the data being provided to you, whether you believe it or not, and whether to ask it to be redone. And it has to be easy to use, otherwise you're not going to be profitable. And one of the disadvantages right now of wavefront guided lenses, and it makes me angry as we move into the marketplace, people like to make lots of money, and I'd like to see it cheaper. Right now they're relatively expensive. Okay, so we need to also identify good measurements from bad and averages, as we discussed, and transmit the data automatically to the design people. Right? These are not simple designs. They're very custom to the individual. So you have to transmit all the information. It's not just series. Okay, so this is an example of the screen of the type of information we get. You can see up here, you can actually see the scleral lesions on the eye. You can see the mark. There's more marks normally that I would consider this a bad picture because you want to see more than one of the marks. But it gives you an idea that you can actually see it. It actually gives you an idea of what the person's actually seeing through that lens, and shows you the aberration structure and gives you aberration structure. Okay, so now assume that you did get all the good measurements and you have this, the wavefront error, you have to send it off to be designed. And of course, that's a complicated process because now you're using a slightly different index material. So you have to take all that into account on the design of the wavefront guided lens. But the key here is, can you make the lens you wanted? So this is a pretty simple diagram. If you get it, this is the design. This is what we wanted. All right, this is the total wavefront error, including sphere and cylinder. So that's why you don't see all the detail. And this is just a higher order aberration. And you can see clearly it's for a keratoconic eye. There's a lot of coma. And then you go over and measure. You say, all right, I wanted that. Did the lens we manufacture actually be that? You can compare total aberration. You can compare the higher order aberrations. And you can see that we get very close to actually creating the lens we wanted. Okay, so the initial goal of wavefront guided corrections is to reduce the higher order aberrations. And this is where I have a real argument with industry because, as I said before, the high order RMS wavefront error doesn't necessarily tell you visual image quality. Right? But the industry would say right back at you, well, the whole design of your system is to reduce the high order aberrations. So the question is, did you reduce them? And that's what clinicians will understand. And then I'm like, well, but clinicians probably really want to understand visual image quality. And so we go back and forth, and of course, the vision scientist loses and industry wins. And so I'm going to show you results in terms of RMS wavefront error and not visual image quality. All right, so here we go. This is pretty easy to follow. I hope once you get it, it'll be obvious to you. So pupil diameter, right? Total RMS wavefront error, that's left, right? In each of these conditions. In-house predicate lens, remember you have to put on a lens, make sure it's stable, then measure the aberrations through that lens, right? And then correct those. So you have to remember, a lot of patients are totally satisfied with just masking. Just put the lens on and they're satisfied. We're dealing with patients that are unsatisfied with that correction. They're not happy with the scleral lens. Okay, so we're comparing the gain from the transitional correction, scleral lens, to a wavefront-guided lens. We're not, on there is not the total aberrations they had to begin with. These are corrections, all of them. So the predicate lens before the wavefront guided, the in-house wavefront guided. So these are all the studies we did in-house prior to actually having a clinician do it. Then we repeat that with the clinical outcomes. And then we have the normal RMS as a function of age for 50 to 60-year-olds. And that's because these are the patients that can afford these lenses. They're established people. The lenses now are costing around $2,000, $3,000 a piece. And I don't like that, but that's the way it is. So you can see the predicate lens here to wavefront guided, predicate, the actual in the clinical population, the wavefront guided, and then normal aberrations at 3 millimeters, same for 4, 5, and 6. Okay, so you can see we're getting people back into the normal range. Okay, and that was for the total. If we focus just on the higher order aberrations, that's what we're trying to eliminate. That wasn't being corrected by just here in cylinder. Again, you can see in the early studies, at the in-house studies, we were reducing the aberrations. Same for the actual clinical compared to normal, the same there, and the same as a function of pupil size. So we're doing a very good job of reducing the RMS wavefront error. Okay, here's the results of one typical patient in the clinical cohort. I show this patient because I've talked with this patient a lot, and I can tell you some of the comments they make. All right, so here's the predicate lens, total wavefront error, and the higher order aberrations, class A to moderate to severe keratoconic. This is a wavefront guided lens, and you can see most of the aberrations were eliminated. Okay, so we can do it. Hopefully I'll show you. I can't remember if I have the slides in there, but we'll see. Okay, the next steps to further improve outcomes are going to be to use visual image quality metrics. While the normalized Zernike polynomial coefficients are mathematically independent, they are not visually independent. Each Zernike mode impacts vision differently, and interactions between aberrations can improve or detract from it. So we don't know if these, we haven't analyzed it yet, and everybody's looking to me to do it, and I haven't done it yet, to see if the actual aberration structures are similar to normal. The total RMS is, but is the actual structure the same? Consequently, the resulting aberration structure of the wavefront guided correction, even though brought to normal levels in terms of RMS wavefront error, may not be impacting vision the same as normal aberration structures in age-matched people. Okay, so then again, I showed this the other day. The visual image quality metrics do a better job than RMS wavefront error and simulating simulated images, and you can take different levels of sphere and spherical aberration, where the total aberrations actually go up, but image quality goes better. And you can do the reverse example where you make it worse. Okay, so the next steps are to compare visual image quality in actual patients fitted with wavefront-guided corrections as measured by the visual strobe ratio to those of H normals. Okay, well, thank you. I thought I had a couple simulations. Well, I showed them the other day in my actual other talk where there was a correction of the keratoconic eye, and you saw that the contrast went way up and the edge sharpness went way up. And these patients really love it. One of the comments this patient made, which is really interesting, because he had naturally fairly small pupils, as Pablo pointed out. You can also use a small pupil in daily life. He had about a 3mm pupil, and he got along well, but he didn't like the image quality. But at night, it's dysfunctional because, you know, things were, he had a large pupil and it was difficult to drive and stuff. And now he said, the comment that I like the best, he goes, now when I come up to a stoplight at night and I look at it, it doesn't have this huge long tail, you know, streaming off of it. It's round like it's supposed to be. And he really appreciates stuff like that. And I can actually read the street signs at night. So it's all, pupil size is really important in all of this. All right, thank you for your time.
So thank you, Ray. I actually have a couple of questions, but they are both related. Good. And very simple. It's when you show the flowers picture for the first time, how many times have you been presenting?
How many presentations? I don't know. I stopped recording them on my CV. So, Pablo, this is the class. My daughter, to give you an idea how long I've been doing it. I can actually do that. This is my daughter, okay, Olivia. I would guess she's, what, say 8 at this time in life. She's now 35. Okay, so these slides, as Pablo points out, I use them constantly. And if you're interested, I'll do a little advertisement for my daughter. She's an actress. Her name's Olivia Applegate. All you have to do is type her name in. She was, if you ever watched America Got Talent, right? TV show in America, but you know, different. She was a singer on American Got Talent, and she was going up and up the ranks, and she quit. She said, "It's all fake, Dad. It's all fake." They pick who's going to win. They were trying to match her in a love life with her guitarist, and they weren't in love at all. They just played music together, and it started really grating on them that every time they got, why aren't why are they talking to the guitarist? Why aren't you guys in love? And the guitarist would say, "We love our music," and be really, really sad about it. So she went up, and then they quit at the quarterfinals because not because they weren't loving it in that way, because they give you the wrong impression. Is that they own you if you win. You've signed a contract that they own you. Neither one of them wanted to be owned. So anyway, she's an actress, and it's good fun. Oh, real questions now.
I hope this is a real question. Okay. If my understanding is correct, some high aberration is good or some are bad, which means that some higher optical aberration would increase the vision, but the others would decrease. And not to mention, all these aberration will interact with each other. So my question is, how can you determine which one should be correct or to keep it there? Yeah.
Yeah. So to answer the first question, any aberration is going to decrease optical quality. Okay. So they all decrease. Some do it less than others, if you're talking about an individual aberration. And even when you add different higher order aberrations together, some of which make the image better, it's not better than perfect. Okay, so You, the way to think about it, if you're going to use aberrations to create a visual benefit like depth of field, right? You gave up something. You increased the depth of field at the cost of contrast or edge sharpness or something. Now, and that's why these multifocal lenses are the most explanted. If you like it, you love it. It met your needs. It met your visual needs, right? And if you're expecting a very sharp image at every distance you look at, you may say, "Oh, I'm not willing to compromise. This is not what it would have."
So are you trying to kill all these higher order aberrations?
Right now, no. What we're trying to do is bring them back to normal. Okay, we're trying to bring them back to the normal range. And my argument with industry right now is let's bring them back to normal visual image quality and not just normal aberration level. Okay, because you could have a mix of aberrations in there that enhance or subtract. And we just haven't done that analysis yet. And I don't know of anybody that has. Am I good?
You good?
Oh, you already did it all. Thank you.
Okay, our next speaker is from the University of Zaragoza, which is about 450 years old, so got an illustrious history. Her talk is going to be on the influence of eye color on corneal densitometry, and her background is in biomedical engineering and physics. Welcome.
Hi, thanks for the intro. You can hear me properly. You don't seem to be complaining, so that's okay. Cool, thanks. Okay, so I'm gonna start sharing my presentation. Okay, I'm gonna share the full screen, might be easier. Yes, you can see the screen? Yeah, and is it moving? Yes. Or, right? Okay, because I don't see you, so I'm just in my presentation. So yeah, I'm a professor at the University of Zaragoza in Spain. I wish I was with you there, guys. But yeah, I have to stay at home, and my presentation is gonna be very different from the sessions that you had previously, because this is not about let's say wavefronts or refractive errors. So yeah, you will see this is about more transparency, corneal transparency. So this presentation is about the cornea. You all know this very well, that we do need the cornea to be transparent because it's a window of the eye, right? This presentation is just about that, the transparency of the cornea, how we can assess it objectively, and which factors might influence to that. So traditionally, this has been done with slit lamp, which is not the best way because it's of course subjective. It depends on the operator, and it's very difficult to follow up because it depends on the clinician that is making the observation. Some years ago, not so long ago, scientific imaging started incorporating what we call the corneal densitometry as a kind of objective assessment of that transparency. And this became kind of friendly, and it's making its place in clinical practice as an objective measure of that corneal transparency. Okay, and this is important clinically, and it has been mostly used to evaluate outcomes of refractive surgery to monitor the progression of different ocular diseases, such as keratoconus, and also in keratoconus, it has been used as an early detector. Because you need to think on this idea of looking objectively at corneal transparency as a very powerful tool because changes in the tissue are always going to happen before than changes in shape. That's why it's interesting for clinicians to have this parameter and being able to rely on it. Okay. And the idea of densitometry is very nice, but short ago we realized there are different doctors that notice that there are different confounding factors that should be taken into consideration before just assessing the, let's say, a given number for a given cornea. So mostly we have age. So the older the eye, it looks less transparent, but this doesn't mean exactly that okay, we know that we use transparency with age, but not as the speed as the numbers show. And this is probably because there are some biometric confounding factors. So the arterial chamber depth is shrink in older people, so it feels that the transparency is lower because this is all based on light backscatter. We also know that the eye tilt influences, so the position of the eye when we are acquiring the measurement. And the newest confounding factor that we found that is kind of obvious, and this is a publication that our group released this year, it's about the brightness artifacts. Okay, so here you have a typical, Seinfeld image in yellow. You have the cornea. In red, we have these outer reflections that this come from the sclera, mostly from the corneoscleral transition. And here in red, we have segmented the iris reflections. This graph comes from these publications, and we saw that this corneal densitometry in the cornea, as we know, it was correlated with age, but also we found that it was a big correlation with both this lateral brightness and with the color of the iris. So we know that that spurious brightness is altering how we see the corneal tissue. But we took one step further, and by the observations that we were doing in the lab while we were collecting this data, we noticed that that reflection that was coming from the iris highly depends on the color of the iris. So this is just an example. This is how an iris, a sample image, would look like from brownish iris, and this is how it would look like from a rather light iris. This is kind of evident, right? Because it was not quantified before what's the influence on the color of your eye in how we perceive the corneal transparency. And that's exactly the objective of this piece of work and this presentation, trying to assess to which point it's important the color of your eyes when we are considering corneal densitometry. Whether it is an important factor that we should be taking into consideration or is just not. So one more thing that so that's the big aim of the presentation, but on the top of that, we of course needed to objectively quantify the color of the iris of each person. So we also proposed a rather straightforward metric with only one number to be able to objectively classify the color of a given iris. Okay, so the methodology, the protocol that we followed, we have 49 color irises and 41 rather dark color irises. We measure them with central imaging, with a tentacam that is, let's say, the staple, the benchmark for assessing corneal densitometry. You know, this device is able to capture images in 25 meridians, and we collect them all. And additionally, to assess the color of the eyes, we used a slit lamp, and we just took a standard photograph of different eyes, like the ones that you have on the screen. Okay, so now our methodology has, let's say, three big parts, three steps. First, the assessment of corneal densitometry. Second, the quantification of those brightness artifacts coming
specifically from the iris, and the third part, the presenting the iris color metric, so assessing exactly what's the color of a given eye, of a given iris. Okay, so how do we assess corneal densitometry? Because Pentagon gives certain numbers, so it gives gain in the software, but it's something that you need, let's say, to pay extra. It's not in all possible Pentacam, so we develop our own code also to have control on what we are doing. So we have those 25 meridians. We segmented the images as I introduced before, separating the cornea, the iris, and the outer reflection. And from the cornea, from this field, so the pixels that compose the cornea, we took the mean pixel intensity. That this is a very simple metric, but it's how corneal densitometry is measured clinically. Okay. And once we have that, we need to assess in the image what's an artifact and what's not an artifact. So to do that, we established a threshold that depended on each image, and it was based on the mean pixel intensity of the cornea and taking the standard deviation over that mean pixel intensity of the cornea. So with this simple equation, we were able to quantify what was which pixels from the image could be considered as noise, as a brightest artifact, and which not in a given percent. We have different meridians per eye, per measurement. So what we do is our achievement for having only one data per eye. And we move on to the slide lamp and to these images. And now the objective is really be able to classify these pictures according to their color. So, okay, we have a standard RGB images, nothing special. And what we do is we move to the CLF color space. This color space has three coordinates, A and B. So as you can see in the image, A grades from green to red, B from blue to yellow, and the L is very useful for this kind of serial images because it gives an idea of the luminance of the image. Of course, we were controlling the illumination conditions, and all measurements, all pictures were taken with the same, outdoors in the same conditions and in the slide lamp with the same settings, but still, as you can see, some images look a bit darker than others. So that's why this was a very useful metric. We have to normalize each component, and this is very important because otherwise the L takes over the A and the B. And for us, it was important that all the three parameters have more or less the same weight. And later, the final metric is as easy as summing up the three normalized components. And with that, we get a single number that illustrates how that is. And here this is just an example. So we saw that the numbers, the eyes, let's say that get a negative score, they are blue eyes. The eyes that get a positive score, they are brown eyes. And the pastel greenish eyes that are in the middle get a number around 0. It can be positive, it can be negative, but this quite simple scale seems to work quite well. And in comparison with other metrics, we get only one number instead of having to work with the three components, which is kind of handy when you want to do statistical analysis later on. So, okay. These are our results, and in our statistical analysis, as you can see here, we have the corneal densitometry, how it is related with the brightness that comes out from the iris. Okay, so you can see that this is already a positive trend, so more brightness, more corneal densitometry. But look what happens if on the top of that we overimpose this iris color metric. As you can see, the bluish eyes are more on the right part of the plot than the brownish eyes. And here we have the comparison of that spurious brightness against the iris color. And as you can see, this is a very, very strong negative correlation.
So the darker the eye, the less reflection. So this is what we were observing. Yes, by capturing measurements in the eye, but we were able to really prove it with numbers. And why is this important? Look, here I brought an example because, as I told you, we've been working on this topic for a while, focused on keratoconic. And from a previous paper, we have this data that, for example, that when you are surpassing a value of 50 in this corneal densitometry, it might be considered dangerous, like a suspect keratoconus. But look at this graph. So this is exactly the same graph that I was showing in the previous slide. And look, everyone, not everyone, but majority of people that fall into that category are people that are having blue, rather blue eyes. And here it's very important to realize that this is not a matter that these people have a less transparent cornea, because of course we assess all of them, we assess them and their cornea look perfectly normal. These people were not wearing contact lenses, were not under medication. All of them were young. We did that to control for that possible factor. So we feel confident that the eye color is really playing a role, and that it should be taken into consideration as a confounding factor when we are trying to objectively assess the densitometry, especially for studies when we are trying to diagnose certain diseases, and we need to take into consideration that the results that are published out there might depend strongly on where was the population, because we know that it depends around the world. People have not we all have the same kind of color eyes. So that's the conclusion, that color light color eyes are too bright even for science. So yeah, some disadvantage, sorry, have to have besides photophobic of having rather bright eyes. So that's all from my part. I would like to thank the team. I did this work with Anna Kuren, who is a PhD student in our group, and I'm really happy to take your questions or curiosities or whatever you want, guys. I will probably stop sharing because it will be easier to
Thanks, Alejandra. Are there any questions?
Hi, Alejandra. Larry Thibos here. Lovely seeing you again. I have a question about I don't know much about Shampoo imaging. I understand it's using white light. But it occurs to me that you might be able to use a colored filter in your imaging system to selectively remove the short wavelength light going into from the instrument and reduce the amount of scatter from those lovely blue irises that shine so brightly. Yeah, blue eyes shine blue because just the same reason the sky is blue here in Africa. Scattered short wavelength light. So maybe you can remove the short wavelengths and reduce your artifact.
technical issue, but sure. I mean, it is a commercial device and it uses blue light. It's not white. So might that influence, or if we use some kind of filter, it might change? Yeah, that's an idea. We could try. Yeah. I'm not sure we could calculate it because as it's a commercial device, I'm not sure how easy it will be to add something on the top of it. But I will try that with some kind of, we do have filters, so let's see how the image looks like. We will give it a chance. Thanks.
To address your question, Larry, it is a narrowband blue wave source. Yeah, it's a narrowband blue LED, I think. So filtering it out makes you blind.
So that why use that?
probably exactly for the reason because it scatters. Because you want to see, originally, Scheinflug was to visualize cataracts.
Right.
So, you know, that makes sense that you want extra scatter. So, and that's also what Alejandra's techniques are based on, exactly on that scatter. If you start blocking the blue and use red instead, it might be less sensitive, right?
Sorry, you'll need to repeat that because the mic is traveling.
Okay, sorry. I'm saying that we also need to take into consideration that this kind of analysis or this interest in corneal densitometry is not only for sample images, but also for OCT, where the image technology is completely different. So, and we will need to check whether this also affects there. Then it will be easier to play with filters or selected wavelength that we want. It might be that we will have less artifacts because one cone of the same flume, then we have a huge artifact from the sclera that we won't have with OCT. Probably for the IEC won't be that strong either.
Any other questions? Okay, thank you, Alejandra, and we'll move on to the next speaker. Thank you. Okay, so the next speaker, Professor Thibos.
I'm already setting up my slideshow. There, a couple of introductory remarks. It's the year 2025 at the moment. We are 25 years into the new millennium, and we are 25 years from the formation of a report from a committee that recommended Zernike polynomials as being the standard for reporting aberrations. My talk today is going to be about an assessment, looking back at those 25 years. Did we do a good job in recommending Zernike polynomials or make things worse for everyone? In celebration of the occasion, I'm wearing the very first Mopane shirt, 1996. And I want to point out it still fits. and for those of you who wonder what Mopane is all about anyway, and this little butterfly looking thing, that's the leaf of the Mopane tree. That's the emblem of the Mopane tree. And the reason that emblem was chosen is because the very first Mopane meeting was held at the Mopane camp in the Kruger National Park. So that's how the name began. In fact, we met several times there in the Mopane camp. So that's a little bit about a history of Mopane.
Still working, all right.
So can you go make it work?
Here.
There it is. Okay. This is that works. Well, it worked for Ray. This is sabotage. It worked for Ray.
There you go.
There it is. Well, sort of. Yeah, how to get rid of that? Oh, there it is. Okay, so you'll see some names there you'll recognize. I have to admit I was the instigator of the formation of this committee, and to try to produce some standards for organizing our community to have a standard way of reporting aberrations. And so what I'm going to do for you is to quickly run through 5 questions that come to my mind in looking back over that 25-year period. Help me give you some background information of how we got to where we are today. So the first one is about why were the standards for reporting aberrations even thought to be important in the year 1999? So the task force was formed. I convinced the Optical Society to call for volunteers, members of the community. Lots of people volunteered. Those are people that were actively involved in measuring aberrations. At that time, clinical aberrometers did not yet exist. So we're talking about researchers with a considerable amount of experience. As we got together, we decided that the task force charge had to be fairly limited. We wanted to articulate definitions, conventions, and standards for issues which were not empirical in nature. In other words, selecting a standard of mathematical functions is a matter of choice. There's lots you could choose from. It's a matter of choice, but we do have to choose to eliminate confusion. And it doesn't require any empirical investigation. So it was a matter of setting those standards for things that didn't require an empirical knowledge. And then everybody was happy with it. I don't have to point my eyes at Professor Applegate here. He wanted us to standardize a few things that we chose not to do that were more empirical in nature. So it was Zernike polynomials, and you know a lot about Zernike polynomials now as a result of all the tutorials you had to sit through. So I'm going to give you my top 10 list, in no particular order really, but it's 10 reasons for why the committee selected Zernike polynomials. The first one, as you know, Zernike polynomials are specialized for circular pupils. If we had square pupils, we might have chosen some other basis functions, and other basis functions had been used in the previous 100 years or so, things like Taylor polynomials and Fourier analysis, and that kind of thing. But we chose Zernike because they were specialized for circular pupils. Second one is that Zernike polynomials were already being used as basis functions in other branches of optics. So in a sense, we were just going with the flow. The people that knew the most were the people in optical design or astronomy, like Dan Neal. You've heard about Dan Neal. He's the one who built that first commercial aberrometer. He was coming from a laser optics lab where they were doing analysis, and he was using Zernike polynomials at that time. And third, the wavefront error function is so easily constructed with Zernike polynomials. That's this notion of being independent fundamental building blocks. It's a weighted sum of Zernike modes. Multiply the Zernike polynomial itself by some weighting coefficient, just add them up. Couldn't be easier. It's an easy way to create a complicated wavefront error function. Reason number 3. The Zernike modes are so beautifully organized into a periodic table, and that helps you mentally organize in your brain how they are organized. And remember, when Fourier analysis, this was the kind of frequency axis that we think about when thinking in the frequency domain. And it's like that's 1 cycle over the circle. This is 3 cycles over the circle, 2 cycles over the circle. And all the ones on the right are the cosines, and the ones on the left are the sines. And they are organized vertically from row 1, row 2nd order. Things are changing as the square of pupil radius. 3rd order, the height is changing as the cube per radius. 4th order, height is going at the 4th power radius. And those fundamental building blocks then are easily conceived, beautifully organized. Let's go ahead and use them. That was the thought. Answer number 5. Why did we choose them? Each mode corresponds to a familiar optical aberration. That's another great plus. And they're listed there. Tilt, prisms, defocus, astigmatism, coma, trefoil, every one is associated with a particular mode. 5 more reasons. Number 6, they are clearly defined. You've seen the equation showing with their length, and they are a complete set of functions that can describe any continuous surface. Now, there could be a limitation, and sometimes you have discontinuous surfaces. Might be some fracture, some change. or with some modern optical designs of things, you can get a discontinuity. Even a simple bifocal lens has a discontinuity between the reading head and the basic power. And so that kind of discontinuity will not be easily handled by Zernikes. But for eyes that don't have those special cases, Zernikes should be able to work pretty well. Mutually orthogonal makes it easy to add up, and you can do a Zernike fit to the data and not be concerned too much about how many modes you choose, because whatever mode set you choose, it's always going to be the least squares fit, the best fitting mode. And if you decide later on to add some other modes, you don't have to recompute the first modes. They're going to be independent of whatever additional modes you might include. So that's a nice property of orthogonality. Number 9, every Zernike mode is normalized to have unit variance. That makes it easy to distribute the total amount of wavefront error into the different modes, because you just add up the sum of squares of the Zernike coefficients. And least squares fitting of empirical data by Zernike polynomial is a simple linear equation. This is for Tanya. Linear optics, look at that. And that beautiful linear algebra calculation. That's the way you compute the Zernike coefficients by a least squares fitting technique. So question number 3 then, why report Zernike coefficients instead of just giving a detailed set of empirical measurements? Well, this is a little more interesting, I think, conceptually. It's all about, well, what do you mean by a report? Remember, the OSA task force was concerned with standards for reporting optical aberrations, right? So what is a report? Well, a report allows an author to inform a reader. The author, so it's like using an information channel. An author writes a report, transmits it to the reader, the receiver reads it, and gets to read the report and gains that information. Now, the information channel could be used to send the raw data. So Applegate here, he thinks we also have an aberrometer which makes 1,000 measurements. And you can send those 1,000 measurements over an information channel, and the receiver can collect them and rebuild the wavefront aberration that had been measured. But that's a lot of data sent over, and there's a lot of redundancy in those 1,000 measurements. So the idea is that a simplified approach, some of the writing here is Windows did a font substitution on me, so some of this stuff might not be readable. The idea is that it's a kind of encoding mechanism. You can think of Zernike analysis as a way to encode the data and make it very efficient. So you may have 1,000 measurements and only send 15 Zernike coefficients, because that includes most of the information to be transmitted. So it's a redundancy reducing method to use Zernike coefficients as your basic information being transmitted from author to receiver. Okay, question number 4. Why did the task force choose to standardize the reporting of wavefront errors rather than, for example, focusing errors? Now we're getting into a little more contentious area. Some of it said before, it's sort of like that was a no-brainer. Of course, that seems like a reasonable thing to do. But this one made people a little bit nervous because we weren't so used to thinking about wavefront errors. The whole field of optometry and ophthalmology was devoted to focusing errors, power, divergence, those kinds of second-order stuff. In fact, one of the chief critics we had was a gentleman by the name of Steve Kleiss. And you've seen this picture a couple of times already here at this meeting. Gentleman here by the name of Steve Kleiss came to the first Mopane meeting. Steve is a good friend of ours and a very competent corneal physiologist. And he made a habit of every time he spoke in a meeting, at least the ones I went to, he would always put up his very first slide. And he would say, microns are for physicists, diopters are for doctors. And he would try to persuade the audience to don't pay attention to those physicists over there. They go around reporting wavefront error in microns. That's not for us doctors. We do diopters, versions errors, and power errors. You see, and in a way, I think Steve was really doing was prodding us a little bit. He wanted to know, be convinced about what it is we should be reporting. Should we be reporting wavefront errors? Should we be reporting power errors? Should we be reporting maybe ray aberrations, slope errors, what we call transverse aberrations, ray aberrations? Maybe we should report those. I think we can appeal to the International System of Units. I like this quote from Wikipedia. You know, there are only 7 base units that describe every phenomenon in the physical world. There are length, mass, time, electric current, temperature, and so on. There's only 7. Now, there's thousands of units being used in science, but they're all derived from these 7 basic units. Right? Now, what is wavefront error? It's a distance. It's a measurement. It's one of the fundamental measurements units in the SCI or in the SI units. So in that sense, I think it's arguably the most fundamental. The wavefront slope, which we call ray aberrations, and curvature, we call vergence errors or power errors. They're all derived from wavefront error. And so the derived units of radians and diopters are less fundamental than just measuring the length. That's the argument for it. Question number 5. This is the last one. Have better ways to specify aberrations and their effects emerged in the last 25 years. So we have not been immune from critics. There have been people who said, no, we didn't do a good job. That wasn't the right way to do it. So I'll just review a couple of the key arguments and criticisms that have been put into the literature. So these are the 3 criticisms. They've mostly been directed at applications and interpretations of Zernike analysis, Zernike coefficients, rather than the primary purpose of reporting. That's what we really wanted to do. We wanted to avoid this. I could just see it coming that everybody was trying to get into the game of doing Zernike analysis, but there were lots and lots of different conventions for reporting. There were different ways of numbering them. There are different ways of naming them. There were even differences in coordinate systems. Those crazy lens designers, they were measuring meridian clockwise from the vertical. Now think about that. This is the optometrists do. We measure meridian counterclockwise from the horizontal. And when so every time that the physicists or this damn Neil were making that aberrometer, his first issue of the aberrometers, they were everything. The numbers didn't make any sense at all. It's because all the cosines have been turned into sines, and all the sines have been turned into cosines, and the angles were all backwards. And he numbered them in the wrong sequence. And it was a mess. You know, we had to talk seriously with Dan about changing his convention. And it was this committee's report that sort of convinced him he had to agree that what we were recommending was going to help him sell his instrument to clinicians. So that is one of the criticisms. But the big one, I think, is that the eye's spherocylindrical refractive state determined from second-order Zernike coefficients do not necessarily agree with subjective refractions. Now, this was a serious concern because people would go to the trade show and Dan would sit in front of his aberrometer, said, I'm going to measure your prescription, do some wavefront aberration analysis, come up with a set of sphere-cylinder axis values. And the patient said, well, it's not my prescription. You know? And what was Dan doing? He was using the second-order coefficients. And it seemed to make sense because we said the second-order coefficients are sphere and cylinder and astigmatism. So why didn't it work? Well, you know why now, because you've seen, where's my picture? Oh, there it is. You've seen this picture a couple of times now that it's kind of unrealistic to think that there is a single focusing criterion that tells you like where's the far point of an eye. Because when an eye has higher order aberrations, those rays coming out of the pupil, every one of them is deflected in a different way. They don't come to a common focus. So if you're interested, for example, in the marginal rays, the focus could be here. The paraxial rays could be down there. A best fitting sphere or the Zernike analysis could be someplace else. But where's the best location for vision? You can't really tell just from an optical analysis like this. You have to appeal to that gold standard of subjective refraction. But now there's an intermediate step. Ray's introduced this a couple of times, and that is measuring image quality. Because the idea is that the best prescription is the one that maximizes image quality. But even that is a little uncertain because there are many ways to measure image quality. And not long after this report came out, Ray and I and our students, we published a paper in which we listed every known metric of image quality. There's no dolls. And there were some 30 of them. Huge number, many, many different ways to measure image quality. So which is the best one? Well, the only way you can tell now is to do that empirical investigation of making measurements of wavefront error, doing the subjective refraction, and then using each of these metrics of image quality to see which one is best predicting the subjective value. And in general terms, the answer is that they all work really well for smallish pupils, say about a 3 millimeter pupil. Virtually any metric you choose, it does a pretty good job. But when you start getting a bigger pupil, things change, and only some of the metrics are giving basically an adequate value, and some are better than others. And so the hunt is on then for what's the best metric of image quality. And the one Ray has mentioned several times, the visual straw ratio, is one that is kind of emerged as being a pretty accurate measure of visual image quality for the purpose of reading eye charts. You have to admit, it's for the purpose of reading eye charts. And there's more to life than reading eye charts. And so it may not be the best metric for vision in general, but it's one that is used. But it helps you boil a wavefront error function down to a single number and make use of that number. It might be a better job. I didn't have it in this diagram because there's just too many of them. And you're like, correction for you. I could have had 30 little spots in here showing you where every one of those metrics thinks the best focus is. And you have to pick the one that is closest to what the subjective is. So in that sense, this criticism, well, although it was given on a number of occasions by a lot of different people, in a sense, it's kind of unfair because the Zernike analysis wasn't really intended for being a refraction machine. It was meant for reporting, so that when I send you some Zernike coefficients, you can deal with them and rebuild that wavefront aberration function without any uncertainty and confusion. So the second criticism we got is using normalized pupil coordinates in Zernike polynomials causes the numerical values of Zernike coefficients to change when pupil diameter changes. And that makes people kind of nervous. Every time you give us Zernike coefficient, so yeah, your spherical aberration is 0.2 microns. I have to tell you the pupil size for which that was measured, because the coefficients vary with pupil size, and that makes people kind of nervous. Why do I have to do that? In fact, I go to the clinic in my university, in the optometry clinic, and they look at the patient recording form where you put down all the information. There's no place where you can write down pupil size. It's like pupil size, optometrists don't care. They make a measurement, they do a subjective refraction. Nobody writes down the pupil size. So we're in a problem there. It's just outside their normal way of thinking. So let me give you a couple of possible replies to this criticism. One is that one of the people on our committee, Jim Schweigling, pointed out a long time ago that Zernike coefficients obtained for different pupil sizes cannot be directly compared. So if you have a 3 millimeter pupil or a 6 millimeter pupil, and you have these two Zernike coefficients associated with those two pupil sizes, you cannot compare them directly. And it's because the pupil, this radial parameter in the Zernike polynomial is a normalized pupil radius. It's not the physical radial pupil radius. So you can't do that, but that problem is easily overcome. If you want to know the actual, put it into physical units, you just have to recompute the Zernike coefficients for some standard pupil size. If you want to compare the little one with the big one, it's usually better to reduce the big one down to the little one. It works better. But there are published formulas that help you recompute Zernike coefficients from one size to another. And after you've done that, then you can easily and directly and legitimately compare the two measurements. A second point by a different author, Philip Stevenson, pointed out, and I think a lot of us have slowly come to understand, that a change in variables from normalized polar coordinate rho that's used in the Zernike coefficients, Zernike polynomials, to the physical coordinate r, this is in millimeters, in a Zernike series is often necessary to answer questions expressed in terms of wavefront vergence and wavefront slope. To do those kinds of calculations, you want to have slope in physical units, not normalized coordinates. But that problem, again, is easily overcome. All you have to do is do a substitution of variables. The Zernike polynomial is written in terms of a rho, but if every place you see a rho, you substitute the radial dimension divided by the pupil radius, big R, then you got the Zernike polynomial written in terms of physical dimensions rather than normalized dimensions for the purpose of computing things like ray aberrations and wavefront vergence. So it's not really a big problem. It's not a serious criticism because it's so easily overcome. And in the abstract that's in the book for this meeting, I worked out a detailed example so you can see how to make that transformation of variables. And I'm on the last criticism to deal with is that other basis functions for wavefront error expansion have superior properties. A number of papers have been published in that area. I've got a quotation here from a few of them. One is about ophthalmic prescriptions in polar vector format can be obtained directly from slope measurements using a new set of orthonormal basis functions called Zernike radial polynomials. And so for that purpose, maybe here's a better basis set, but I wouldn't let you use it for reporting the aberrations. It's only for the purpose of computing the ophthalmic prescriptions. There's a second comment. Bessel circular functions are an alternate method, better than Zernike circle polynomials for some important cases of corneal surfaces, influence functions, and the complete anterior corneal surface. Well, what do we say to that? Well, fine, if that's what you want to do, you can use Bessel functions, but they're not for reporting the data, but for using the data for that purpose. And remember that these Zernike polynomials were set up to describe shape. You can just use the Zernike polynomials to describe the shape of the cornea, and people are doing that. And that's just fine. And maybe Bessel functions will be better for interpreting the results or for clinical applications, but you don't want to call them they're not consistent with the standard for reporting aberrations. And a third example, a new aberration series. This is Damien Gatanel from our, has been to many Mopane meetings before. He's not there today. A new aberration series is proposed to better separate low versus higher order aberrations, quantify aberrations more accurately, and be a better measure of the impact of clinically significant aberration modes. At the last was at the last Mopane, last VPO meeting, maybe 2 meetings ago. Damian presented this work showing his new series, and he said it had better, superior qualities. So what's he worried about? Let me show you what he's worried about. These are the Zernike polynomials, remember, and it's all about balancing higher orders with lower orders. Let me show you a good example. This is the Zernike mode polynomial for spherical aberration. Notice it's got a rho to the 4th power term. That's what makes it a higher order aberration. The steepness of this function is growing rapidly. That's r to the 4th. But included in that polynomial is you're going to subtract off a certain amount of rho squared. And what's rho squared? Well, rho squared is this one, defocus. So the way you make the Zernike mode for spherical aberration is to take a r to the 6th curve, which people traditionally called Seidel spherical aberration. That curve, that surface is going to grow rapidly as r to the 4th power. But then subtract off some defocus. So you end up, instead of having this lovely 4th order curve going up like that, when you subtract off some defocus, it goes instead. So what's going on here? Why are we doing this? Well, the reason Zernike did it was to make sure that this mode was orthogonal to defocus. And it had to subtract off some of that defocus, had to put in that 2nd order term in order to make the terms orthogonal. And you had to make them orthogonal so they'd be independent. It's kind of an obligation. But for interpretation purposes, people worry about it, thinking, well, some of my defocus is in that spherical aberration term. So maybe I should collect all the defocus terms from spherical aberration and even 6th order spherical aberration and bring them all together with 2nd order defocus and add them all together. That would be a better method. So, well, maybe that's a better method. Maybe it's not. But it's all to do with the application of these modes, not the specification of the mode. It's not for reporting purposes. So there may very well be a better way to make use of the data by such a technique of collecting the R squares. I don't know. But it has led to some interesting paradoxes. Now, I'll show you an example of one. Balancing, the good and the bad of this balancing phenomenon. So balancing is necessary to make the lower order modes mathematically orthogonal. I already mentioned that. And balancing can reduce optical wavefront variance. And that's true. If you think about this r to the 4th, it's going along flat in the middle of the pupil. You go, oof, r to the 4th. It goes whopping a very rapid, huge variance. What does balancing do? It spreads that variance out more evenly across the pupil so that some of the variance is at the margin is not nearly so big now, but you've got more in the middle of the pupil. So that turns out to be not very good for vision. So the paradox is that you reduce the wavefront variance, which seems like a good thing, but it reduces performance, which is a bad thing. And that's the kind of paradox that Tanel was worried about. Balancing also enables easy bookkeeping of wavefront variance. It's the sum of individual modes. That sounds like a good thing. That's a good property. But increasing total variance sometimes actually improves image quality according to other metrics. And that's the case for spherical aberration. Yeah. So you're better off for vision of having the middle of the pupil nice and almost very little wavefront error over that central area, and let most of your wavefront variance go out near the margins of the pupil. That actually produces a better image, produces better vision, and by some metrics, produces better image quality as well. So there are some worrisome issues that are frequently debated. And my feeling is that these worrisome issues, we will slowly come to understand what they are through experience. And this is my opportunity here to make an appeal for people in your cohort now to take advantage of this new millennium. New technology has developed. You see, in the 20th century, in fact, for the first 2,000 years of recorded history or whatever, it was very, very difficult for a clinician to understand the optical limitations to vision for an individual person. That's because I can't see the retinal image on your eye. So you may have some horrible optics like that, and you complain bitterly, you go to the doc, I can't see well, what's the problem? Gee, I'd love to be able to see your retinal image, but I can't. Yeah. And not many people could, before the year 2000, not many people could see. I think one is, this guy over here, Pablo Artel, he had the ability and the technique available to put a spot of light on the retina and had a camera sensitive enough to actually see it and record it. So he could see the point spread function of an individual eye in his research lab. And the other person I think it was 400 years before Pablo, Christoph Scheiner. Remember what he did? He took that eye from a sheep, dissected it, and pulled it all in, and dissected it, pulled it off the sclera, and saw the retinal image on the back of the eye. Now, why am I suggesting that you folks have the ability? It's because you can compute the retinal image. You see, by measuring these wavefront aberrations, you do the kind of stuff that Applegate's been showing over and over again. Pictures of eye charts, pictures of people, pictures of anything. You see, the stimulus to vision is not the external world. You might think it is. You might think the stimulus to vision, is the picture on that pamphlet there, or it's the image on your cell phone, or it's the eye chart on the wall. That's not the stimulus to vision. The stimulus to vision is the retinal image. And so you have to get through the optics and finally get a retinal image. Now the visual system has something to work with. Try closing your eyes sometime. The world's still there, but there's no vision, is there? You haven't got a retinal image. So I want to be able to see your retinal image as a practitioner. I'd really love to know why you're complaining. What's your problem? And whether or not my prescription for your complaint is going to work. You see, I want to be able to do that. And so, although I can't get my microscope inside your eye and look at the retinal image directly, I can compute it. And that's the value of the modern technology. As a 21st century doc or scientist, you now have the ability, the technology necessary, the mathematics, methods, it's all published, it's in the open domain. All you have to do is make use of it. Now, as we said before, as we were talking about, what's the best aberrometer to buy to do all this work? Docs have a lot of say into how the engineers and the companies make their instruments. If the doc says, I want a really nice display of the retinal image for some standard, like an eye chart, I want to see that. I just want some pretty artist impression. I want to see the kind of image he's showing of the eye chart. Then eventually the manufacturers will do that. They'll say, this is what the docs want. And so we'll make it available. There's no reason why they shouldn't. So you're knowledgeable enough now to know, I want to compute the retinal image for my patient's eye for the aberrations I just measured. And then that will make it possible for you to inspect the image and hopefully gain some appreciation for why it is people don't see well. So that's my pitch. I hope that you can make use of your expertise, newly gained expertise in the art, technology, and purpose of wavefront aberrometry. And did we do the right thing? Well, of course, I think we did the right thing. The conclusion, Zernike analysis as recommended by this, it's an ANSI standard, it's an ISO standard, it's the one you've been learning about. I think we did the right thing. It's an unambiguous way to report data. Now, those Zernike coefficients indicate the relative contribution of each mode to the wavefront error. They don't necessarily signify the relative importance of information of the individual modes. It's a point that Ray has made over and over again, because they interact with each other. And depending on the user's purpose, There might be a very good reason for taking those wavefront error measurements and using a different method of representation, maybe change from from normalized coordinates to physical coordinates, whatever you need to do. It'd be perfectly justified. But it's not a criticism of Zernike polynomials as being the standard. Okay, it's lunchtime. Oh, Ray, you have a question or a point, comments you want to make?
So Larry mentioned at the very beginning that I had a very strong objection to this system, not Zernike polynomials, but in our original report, and this is got lost in the ANSI standard. In the original report, I was wanting to demand that you had to use the center of the pupil as the center of your coordinate system, and that had to be 0, 0, right, for all of the calculation purposes, and that got lost in the ANSI standards. So if somebody picks a little different center, then you're going to have different Zernikes, and you can't compare instrument to instrument. So to me, it was critical that we demand that the coordinate system be fixed to the center of the pupil. And in our original report, we did specify that it had to be the center of the pupil, right? And as Larry pointed out that a lot of people use the dots and didn't capture it to determine the center, right? And didn't capture the actual pupil to determine the center. Well, in my role as advisor to companies, I demand that they have a picture of the iris so that we know where the pupil center is, right? Because you actually want to throw data away right at the edge because it's clipped often by the pupil edge. You don't want to use that data. So anyway, capitalizing on what Larry said, doctors, if they're knowledgeable, can demand it, right? You're going to have the power when you start using aberrometers as the field matures, saying it's got to be done right, And I strongly feel that dropping where 0, 0 is a critical error for reporting.
Right. And another, I didn't really mention it because this topic was about Zernike polynomials, but the coordinate system also was an important thing. It's not just about measuring meridian in the right direction, but it's about these multiple use instruments now where you're doing corneal topography and wavefront aberrometry in the same instrument. Okay, well, what's the common reference axis? See, for aberrometry, this reference axis is not the optical axis, it's the line of sight. It's the line of sight. It's the line connecting this fixation point to the center of the pupil. Line of sight. So if your corneal topographer uses something else, let's say a ferrometric axis, which is what an awful lot of corneal topography does, it's based off the Kinsey images and making sure that the ingoing light is perpendicular to the cornea. That's a different reference axis. So you're going to have a great deal of difficulty of accounting for the wavefront aberrations based on the corneal shape. They should have the same reference axis. And that's been a message that's been difficult to communicate with the manufacturer because it's easy to line up a corneal topographer based on Purkinje images. It's harder to get it to line up according to the line of sight. But for comparison purposes, it's important that you do that. So. Any other questions? Pablo, you want to make a comment?
Very quick. Very quick, 2 comments actually. One is about you mentioned about a pupil size, and I think this has been one of the main problems. I don't know how this can be incorporated more in the standard, right? But one of the main problems we have is so many papers, so many reporting of wavefront aberration without the pupil size data, right? And I have a trick for the young people. If you have a paper like this, then you just stop reading. You know that it's not going to be very good. because they are missing something very important, but it's very common. And the other thing that is a problem, and it's not here, is Zernikes are not good for reporting very small details. If you want to keep very high order aberrations, super high order, don't use Zernikes because, well, you need to go so many terms, right? And never get exactly. There is also paper that they say, well, we are reporting until the 100th order of Zernike polynomial. Well, don't do that. You just go point by point. You do a different thing. You do not fitting of polynomials. You do just direct point by point data. That would be basically my two comments. But I think this has been a big success. So this standard for the exam.
And that's especially important for using wavefront aberrometry in the analysis of the tear film. You know, the tear film is the first optical component of the eyes optical system, and it's a very important component. It's probably the most important. If you've got a bad tear film, that's the most important source of aberrations of your whole eye, tear film. And what are the tear film aberrations like? Well, they tend to be extremely specific. They're very localized, and they can be almost discontinuous. Like you've got a little hole there where the tear film has broken up, and you're exposing bare cornea. And so the aberrations, in order to render them accurately, you need a very high resolution aberrometer, like Ray saying, thousands of points. And you still might not be able to have a Zernike series that will capture those local points unless you report 1,000 Zernike coefficients. So at that point, it's not really very efficient, I have to admit. You're not reducing the amount of information you have to transmit. You might just as well report your 1,000 measurements. So there are circumstances where it's just not going to be advantageous.
Something that connects to Pablo's question. Something I never heard actually is that the resolution that you get of the overall image is not uniform in a Zernike reconstruction, because these radial wobbles, they tend to be much more violent towards the edge of the pupil rather than in the center.
Yes.
So if you would have something like a corneal scar somewhere central, right, you would need many more Zernikes to do that accurately, rather than if that same scar would be somewhere in the periphery.
Yeah.
You know, that's one comment. A second comment is I see it a lot less, but during the early days of wavefront aberrations, there were lots of doctors that thought, okay, now I can just treat the trefoil. That one is a bit too high, so I can just treat just that one, and the eye will be perfect. Not realizing that, okay, they may be mathematically independent, but it's a physical structure, you know, with biomechanics. And if you just treat that trefoil, everything changes. So they were confused. So I see that a lot less nowadays, because this kind of perfect vision ideal from 20 years ago has been abandoned, luckily. But still, a lot of medical doctors seem to be confused by the Zernikes, even so after 25 years.
Yeah. Anybody else comment? Right?
No, another way to say what John just said, and that you know, the optics are the first stage of vision, and if you don't consider, you know, what the visual system does to it, right, then you're mistaken. So you don't need a perfect image, right? And a lot of people misinterpreted our book when we said, "Oh, the quest for supervision." It was really the quest to present the best visual image to the system, right? And that's the problem with words. You know, the people will interpret the words as if we created a perfect image that the brain could do it. No, we have sampling limits, right? And if you undersample the image, yeah, well, you undersampled it.
What can you do about that?
That's what you can do about it.
That's the topic for tomorrow's talk, undersampling. I'm not going to talk about optics anymore, but I got one more talk to make. Okay, I think we're finished. I'm like, oh,
Yeah.
no.
2:45.
2:45. Yeah.
Okay, so we're going to break and then be back at 2:15. 2:15.